Four elements: earth, air, fire, water. Imagine standing at the edge of an ancient marketplace in Athens. The air is full of dust, olive oil smoke, voices calling out prices for figs and wine. On the stone steps a man speaks, not about trade or politics, but about the fabric of reality itself. He points to the sky, the ground, the flame in a brazier, and the breeze rolling through the square. Four things, he claims, and nothing more. The world in all its complexity rests on just four elements: earth, air, fire, and water. This idea, born in the fertile centuries before modern science, had a strange clarity. Everything solid and unmoving was earth. Everything fluid and shifting was water. Everything that vanished into smoke or could rise as heat was fire. And the invisible, untouchable substance that filled the lungs and moved the clouds was air. With these four building blocks, philosophers like Empedocles thought they had reduced chaos to order. It is easy to smile at this today, with our periodic table, our subatomic particles, our fields and quarks. Yet for centuries, the four elements were not superstition. They were the dominant scientific framework across Greece, Rome, the Middle East, and Europe. Physicians diagnosed illness through their interplay. Alchemists sought transformations among them. Artists, poets, and mystics spoke of them as the architecture of existence. To understand the four elements was to grasp how matter, life, and even the soul moved. The theory had an elegance modern chemistry sometimes lacks, where we have a table of over 100 symbols, most invisible to everyday experience. The ancients had a system anyone could see. Hold soil in your hand. Earth. Drink from a stream. Water. Watch a torch fire. Feel the wind. Air. It was intuitive, visible, and portable across cultures. The simplicity made it powerful, and that power gave it longevity. It lasted more than 2,000 years. Empedocles, who gave the theory its classic shape in the 5th century BCE, imagined these elements not as random but as eternal substances, mingled and separated by two great forces he called love and strife. Love brought elements together, forming bodies, mountains, and seas. Strife tore them apart, returning things to dust. In his cosmology, even change itself became a dance of elements, guided by cosmic affection and enmity. Aristotle later modified this vision, blending the four elements with his system of qualities: hot and cold, dry and wet. Fire was hot and dry. Water cold and wet. Air hot and wet. Earth cold and dry. With these polarities, he believed, one element could transform into another. Heat water enough and it evaporates, becoming air. Burn wood and it turns to fire. Then ash, returning to earth. He was not so far from real transformations. He only lacked the hidden machinery we later uncovered. For physicians, the four elements became the mirror of the body. The Greek doctor Hippocrates and his followers paired them with the four humors: blood, phlegm, yellow bile, and black bile, believing health was a matter of balance. A fever was an excess of fire. Melancholy, too much of earth. Cheerfulness, a dominance of air. It gave doctors a logic, a way to interpret symptoms and prescribe cures. Whether by diet, herbs, or bloodletting, they sought to bring the inner elements back into harmony. In the Middle Ages, scholars wove the elements into theology. Fire was divine energy, air the breath of spirit, water the cleansing sacrament, earth the humble material of Adam's body. Alchemists tried to manipulate them, searching for transformations that would yield gold or immortality. Poets mapped them to the temperaments of human character: a fiery soul, an airy dreamer, a watery heart, an earthy mind. Even now, fragments survive in our language. What is striking is not that the theory was wrong, but how it shaped habits of mind. It trained people to seek patterns, to unify experience under a small set of principles. The desire for simplicity has not vanished. When we speak of the four forces of physics or the double helix of life, we echo that same craving to compress the infinite into something we can hold in thought. Why did it eventually collapse? Experiments accumulated that could not be explained by the four elements, the discovery of oxygen, of chemical reactions that added or lost weight, of conservation laws. All these chipped away at the elegance. By the 17th century, chemistry demanded more than four names, and yet, for centuries, the system had been serviceable. You could live an entire life, treat patients, compose poetry, design rituals, all under the elemental canopy. There is a lesson in its endurance. Our best frameworks are always provisional. Today's tables and theories may one day look as quaint as earth, air, fire, and water. What seems obvious now may be forgotten scaffolding later. Knowledge moves forward by forgetting as much as by remembering. And yet, there remains something archetypal in those four ancient pillars. We still speak of being grounded, of fiery passion, of airy ideas, of flowing emotions. The old categories haunt the psyche even as they have left the laboratory. Perhaps they survive because they touch the senses more directly than atoms or quarks ever will. Picture again that marketplace in Athens. Earth beneath your sandals, water in clay jars, fire flickering on torches, air swirling through the square. Four presences, always near, always shaping life. An old theory, now forgotten in science, but still alive in the metaphors we live by. Humorism, balance of bodily fluids. In a candlelit chamber, 2,000 years ago, a physician leans over his patient. There are no microscopes, no germ theory, no antibiotics waiting in bottles. Instead, the doctor places fingers on the wrist, studying the pulse. He examines the eyes, the tongue, the complexion. Then, with grave confidence, he diagnoses the imbalance of fluids within. Health, he explains, is harmony among four humors: blood, phlegm, yellow bile, and black bile. Illness is discord. Cure means restoring balance. This was humorism, the dominant medical theory of the ancient world, born from Greek thought and carried through Rome, the Middle Ages, and even into the Renaissance. To us it seems quaint, even grotesque. Yet for centuries it framed the way doctors and patients understood life, health, and the very nature of personality. The humors were paired directly with the four elements. Blood, warm and moist, was the counterpart of air. Phlegm, cold and moist, mirrored water. Yellow bile, hot and dry, matched fire. Black bile, cold and dry, belonged to earth. Just as the cosmos itself needed balance, so too did the body. Each humor carried not only a physical role, but also a psychological weight. From this grew the four temperaments: sanguine, phlegmatic, choleric, melancholic. A sanguine person, dominated by blood, was cheerful, sociable, full of energy. A phlegmatic temperament with abundant phlegm suggested calmness, sluggishness, perhaps reliability. A choleric nature tied to yellow bile was fiery, quick-tempered, ambitious. And a melancholic soul, carrying excess black bile, was thoughtful, serious, often sad. Even today, these adjectives cling to us. We still call someone sanguine when they seem optimistic, or melancholic when sadness shapes their mood. Humorism was not an idle philosophy. It guided treatments, sometimes harsh, sometimes oddly effective. Bloodletting was the most famous. If fevers rose, physicians assumed blood was excessive, so leeches or lancets drew it out. For lethargy, purges and vomits expelled phlegm. Diet, too, was prescribed to balance humors. Hot, spicy foods could counter cold, sluggish phlegm. Cooling fruits or herbs subdued fiery choler. Every recipe became a form of medicine. Every meal was therapy. The theory shaped everyday language and culture. Playwrights like Shakespeare built characters around the temperaments. This fellow is sanguine, one might say of a comic figure. That nobleman is choleric. Another whispers before a duel. Doctors spoke with the authority of cosmic harmony, diagnosing with metaphors as much as measurements. For many centuries, this was medicine's grammar. Why did humorism last so long? In part because it felt sensible. Everyone could see fluids, blood, phlegm, bile in their own bodies. Illness often produced changes in them. The idea of balance matched what people observed in weather, crops, and society. Harmony was health, imbalance was disorder. And medicine, like philosophy, craves patterns. Humorism offered a system. It also provided a bridge between body and mind. Instead of treating mood and illness as unrelated, the theory united them. Sadness, anger, joy, lethargy, all were not just spiritual states, but physical conditions of fluids. In a way, humorism was holistic. It suggested that to treat the body, you must understand the soul, and to treat the soul, you must attend to the body. Of course, the theory was flawed. Bloodletting often weakened patients fatally. Purges and vomits did more harm than good. The humors could not be measured, only inferred. As anatomy advanced, as Harvey discovered circulation, as microscopes revealed cells and microbes, humorism faltered. By the 19th century, germ theory replaced fluids with pathogens. The invisible causes of disease became known, and the old fluids were relegated to history. But humorism left a residue. Its language shaped psychology. Temperaments became personality types, long before modern psychology divided traits into 5s and 6s. Therapies still speak of balance, harmony, homeostasis. Even the modern emphasis on lifestyle, food, exercise, rest, as preventive care has faint echoes of the old doctrine. Doctors still advise diets not unlike the balancing acts of humoral medicine, though the science behind them has changed. There is something deeply human about the theory's persistence. We crave balance in our health and our days. We speak of being off balance when stressed, in harmony when well. Humorism gave shape to that intuition. It told a story that felt close to lived experience, even if the mechanics were wrong. Imagine again that patient in the candlelit chamber, hearing the physician's words. Perhaps the diagnosis offered comfort, a sense that illness had meaning, that suffering could be named and treated. Perhaps the rituals of bloodletting or herbal prescriptions, though misguided, carried placebo power. The human body, after all, often heals itself if given time and rest. The belief in balance may have given patients the strength to wait. Today, humorism lives only in textbooks and metaphors, but it reminds us of how fragile knowledge is, how even error can rule for centuries when it feels intuitive and elegant. It shows how science evolves not by mocking the past, but by building on its instinct to find unity, to explain life in patterns, to heal with meaning as well as method. And if you listen closely, you still hear its whispers. In the words sanguine and melancholic, in the advice to balance work and rest, hot and cold, energy and calm, in the quiet hope that our bodies, like the cosmos, can find harmony again. Geocentrism, Earth at the center. Picture yourself standing on a hillside in the ancient world. The sun rises in the east, sails across the sky, and sinks in the west. The moon follows its own slower path, waxing and waning with steady rhythm. Stars wheel around the night like a vast dome turning overhead. To the naked eye, one thing is beyond doubt. Earth is still solid, unmoving. Everything else dances around it. This belief became the heart of geocentrism, the idea that Earth rests at the center of the universe. It was not a fringe notion, but the ruling scientific framework for nearly 2 millennia. From Aristotle's philosophy to Ptolemy's detailed astronomy, geocentrism offered a system that explained the heavens with logic and precision. It was not only a map of the cosmos, it was a worldview that gave human life central importance in the cosmic stage. The Greek philosopher Aristotle laid the foundation in the 4th century BCE. He described the universe as a series of concentric spheres, with Earth immobile at the core. Around it revolved the moon, the sun, the planets, and the fixed stars, each attached to its own crystalline sphere. Motion was circular because circle was considered the most perfect shape. To Aristotle, Earth belonged to the realm of change and decay, while the heavens were divine, eternal, and unchanging. Several centuries later, the astronomer Claudius Ptolemy refined this model in his Almagest. The problem was that planets did not move in perfect circles as expected. They sometimes slowed, stopped, and even reversed direction across the sky, retrograde motion. Ptolemy solved this with a clever device: epicycles. Planets, he suggested, rode on small circles, which themselves revolved along larger circles around Earth. With enough epicycles, the heavens' odd motions could be predicted with remarkable accuracy. His geocentric model became the most advanced astronomy of its time. Why did geocentrism hold such sway? First, it matched everyday experience. Stand still, and the world feels stable. Watch the sky, and everything else seems to move. No one felt Earth spinning beneath their feet or hurtling around the sun. Second, it carried philosophical and spiritual appeal. If Earth was the center, humanity was not adrift in a meaningless expanse, but placed at the heart of creation. Religions folded the model into their teachings, seeing divine order reflected in celestial circles. For centuries, geocentrism guided calendars, navigation, and astrology. Priests and scholars tracked the sky using Ptolemy's tables, predicting eclipses and planetary alignments. Astrologers read the heavens not only as a clock, but as a book of destinies, each planet's motion tied to human fate. The geocentric cosmos was both scientific and symbolic, mapping not only stars but also meaning. Yet cracks slowly appeared. Islamic scholars in the Middle Ages refined and questioned Ptolemy's system, noting that its complexity hinted at deeper flaws. By the Renaissance, the model's countless epicycles looked more like patches than elegance. Then came Nicholas Copernicus, who dared to place the sun at the center. His heliocentric model explained retrograde motion without epicycles. Planets were not backing up but simply being overtaken as Earth itself moved. Still, Copernicus's idea spread slowly, resisted by both tradition and the senses. The real shift came with Galileo Galilei and his telescope. He saw moons orbiting Jupiter, proving that not everything revolved around Earth. He observed phases of Venus, impossible under Ptolemy's system, but natural in Copernicus. Evidence piled up, and geocentrism faltered. By the time of Kepler and Newton, the Earth-centered cosmos had been overturned. The planet we stand on was no longer the hub, but one body among many, circling an ordinary star. Geocentrism, though wrong, is a powerful reminder of how convincing appearances can be. The sky does look as though it turns around us. Our senses tell us we are still. It took centuries of questioning, measurement, and courage to move beyond that illusion. Science often advances by doubting what feels obvious. And even as a forgotten theory, geocentrism lingers in language and imagination. We still speak of sunrise and sunset, though we know the sun does not move. We instinctively describe ourselves as central, our view as privileged. The old model haunts the human mind because it flatters us, placing our lives in the middle of everything. Perhaps that is why its fall was so profound. The Copernican revolution was not just astronomy, it was philosophy. It displaced humanity from the cosmic throne and taught us humility. We orbit, we spin, we drift. Our planet is a speck in vastness. And yet, paradoxically, knowing this makes our lives feel both smaller and more precious. So imagine again the hillside, the stars wheeling above. For most of history, the people who gazed upward believed the whole sky was circling them. They were wrong, but their error was understandable, even poetic. Forgotten now, geocentrism is a monument to the human tendency to trust the senses, to believe in centrality, and to cling to models that make us feel important. Epicycles, planets on circles of circles. Step outside on a clear night and trace a planet's path across the sky. Night after night, it drifts steadily against the background of fixed stars. Then, without warning, it slows, halts, and begins sliding backward. This strange reversal, retrograde motion, was one of the most confounding puzzles in ancient astronomy. How could heavenly bodies, thought to be perfect and eternal, stumble in their courses? The solution, offered by Claudius Ptolemy in the 2nd century CE, became one of the most elaborate constructions in scientific history: epicycles, circles upon circles. According to his Almagest, planets did not simply orbit Earth in single loops. Instead, each planet was mounted on a small circle, the epicycle, which itself revolved along a larger circle called the deferent. As the planet traced its epicycle while the epicycle spun along the deferent, its apparent path wavered like a looped ribbon, producing the backward drift seen from Earth. It was an ingenious model, not because it was true, but because it worked. With enough epicycles layered onto each other, astronomers could predict the positions of planets with surprising accuracy. Calendars, eclipse forecasts, and astrological charts all relied on these calculations. For over 1,000 years, epicycles were astronomy's reigning tool, accepted from Alexandria to Baghdad to medieval Europe. There was elegance in its complexity, at least at first. The heavens, philosophers said, must move in circles, the most perfect of shapes. If circles did not fit reality, then more circles must be added until they did. The sky became a grand machine of nested wheels, each turning another, a cosmic ori invisible but exact. Monks and scholars constructed astronomical tables that guided navigation, agriculture, and ritual. Yet beneath the precision was a growing unease. As centuries passed, the system required more and more epicycles to match observation. Mercury and Venus demanded intricate adjustments. Mars proved especially unruly, its retrograde stretching the model nearly to breaking. By the late Middle Ages, the cosmic machine looked less like divine perfection and more like an ungainly contraption patched with gears. What began as elegance turned into clutter. Still, the epicycle model endured, and its endurance reveals something about human thought. We often preserve a framework long after cracks appear, adding patches rather than questioning the foundation. The theory had institutional weight, religious endorsement, and the comfort of tradition. To abandon it meant not only changing astronomy, but also unsettling philosophy and theology. It was safer to keep adding circles. Then came Nicholas Copernicus in the 16th century. By placing the sun at the center, he explained retrograde motion without elaborate epicycles. As Earth overtook other planets in its orbit, they only appeared to move backward. Copernicus still used some epicycles to maintain perfect circles, but far fewer. The idea was radical, but its simplicity was a quiet revolution. Later, Johannes Kepler abandoned circles entirely, introducing ellipses. The planet's strange loops vanished into the clean logic of orbital mechanics. What Ptolemy's spinning wheels once mimicked, Newton's law of gravitation finally explained. Epicycles became relics, a memory of humanity's long effort to preserve a theory past its usefulness. And yet, the metaphor of epicycles lives on. We use it to describe any overly complicated fix layered onto a shaky foundation, when bureaucracy grows unwieldy, when software is patched instead of rebuilt, when excuses multiply to save a crumbling argument. To say this is an epicycle is to warn against clinging to elegance that no longer explains reality. There is something both tragic and beautiful in their story. Tragic because so much brilliance was spent refining an illusion. Beautiful because that very refinement kept the embers of observation alive until a new model could replace it. Epicycles are a reminder that error is not wasted, it is scaffolding. Without them, astronomy might never have accumulated the data that allowed Copernicus and Kepler to see differently. Imagine a medieval scholar hunched over parchment, copying planetary tables by candlelight. He believes in crystalline spheres, in Earth's stillness, in the divine harmony of circles. Yet his work, the painstaking correction of planetary positions, will eventually help prove him wrong. His devotion builds the library that fuels a revolution. In this way, epicycles belong not only to a forgotten science, but to the long lineage of progress itself. Today, when you see Mars linger and backpedal in the sky, you know it is Earth's own motion creating the illusion. But if you squint, You can still imagine Ptolemy's wheels turning, intricate and patient, trying to preserve a universe that always seemed to circle around us. They remind us that knowledge often advances not by leaping straight to truth, but by circling through error, looping and looping until the path opens forward again. Spontaneous generation of life. Picture a farmer in ancient Greece stacking hay, or a baker in Renaissance Italy leaving dough uncovered on a warm counter. To their eyes, the world seemed full of self-creating wonders. Maggots wriggled from rotting meat. Mice appeared in grain bins. Flies seemed to arise from piles of manure. Life emerged, uninvited and unexplained, as if decay itself carried the seeds of animation. This was the belief in spontaneous generation, the idea that living creatures could arise from non-living matter. For most of human history, spontaneous generation was not a fringe superstition, but a common-sense conclusion. Who could watch worms crawl from soil, or fleas erupt from dust, and not suspect that life sprouted directly from its surroundings? Philosophers and physicians built elaborate theories to explain it. Aristotle, in the 4th century BCE, gave it formal shape, suggesting that animals could be generated spontaneously from dew, slime, or decaying flesh, provided the right mixture of warmth and moisture was present. To him, life was abundant, constantly renewed by nature's own fertile processes. The theory endured through the Roman Empire into medieval Europe and across the Islamic world. It seemed to match daily observation. Grain stored carelessly produced mice. Pools of standing water bred frogs. To most people, this was not puzzling, but obvious. Why imagine tiny, invisible eggs or parents hidden from sight when the evidence seemed plain? Life burst forth because the world itself was alive. During the Renaissance, spontaneous generation was still taught as accepted science. Recipes circulated, half serious, half curious, claiming one could create mice by placing a dirty shirt in wheat or generate bees from a dead ox. While exaggerated, these tales reflect the deep conviction that life did not always need parents. It could emerge when conditions aligned, a gift from nature's hidden powers. Yet doubts slowly crept in. The 17th century brought the first cracks. Thanks to the microscope, Francesco Redi, an Italian physician, performed a simple experiment in 1668. He placed meat in jars, some sealed, some covered with gauze, others left open. Maggots appeared only in the exposed jars where flies could lay eggs. When flies were kept out, no maggots grew. Redi concluded that larger organisms did not spontaneously arise. Life came from life. Still, resistance lingered. Many conceded that maggots needed parents. But what of smaller, simpler life? Microscopic organisms, now visible through new lenses, seemed to appear from nowhere in boiled broths or infusions of hay. Perhaps spontaneous generation still operated at the tiniest scales. For another 2 centuries, the debate simmered. In the 18th century, John Needham, an English naturalist, boiled broth, sealed it, and still found microorganisms growing. To him, this proved life could spark spontaneously, at least among microbes. But soon after, Lazzaro Spallanzani, an Italian priest and scientist, repeated the experiments, boiling broths longer and sealing them more tightly. No organisms appeared. He argued that Needham's flasks had been contaminated. The controversy sharpened. Was it life from life or life from nothing? The decisive blow came in the 19th century with Louis Pasteur. Using swan-necked flasks, he boiled nutrient broths and left them exposed to air but shielded from dust by the flasks' curved necks. The broth remained clear, free of life, unless particles from outside reached it. Pasteur's work showed that microbes did not materialize from broth, but arrived from the environment. Life, he declared, comes only from life. Omni vivum ex vivo. With this, spontaneous generation was finally laid to rest in science, though not in imagination. Why did it survive so long? Because it offered an elegant answer to a difficult question. Where does life come from? Without the tools to see eggs, spores, or microbes, spontaneous generation seemed obvious. It also aligned with deeper beliefs that nature was endlessly fertile, that decay and death fed new life. Even today, the compost pile and the blooming field whisper that death nourishes life, though we now understand the cycles in terms of decomposition and reproduction. Interestingly, the question that animated spontaneous generation has not vanished. Pasteur's victory closed one door, but opened another. If life cannot arise from nothing under ordinary conditions, then how did the very first life appear on Earth? Scientists today explore abiogenesis, the origin of life from non-living chemistry billions of years ago. In a sense, modern research circles back to the same wonder. How can matter organize into cells? How can chemistry become biology? The answers differ, but the question remains timeless. Spontaneous generation now belongs to history, a forgotten theory once woven into daily life and learned scholarship. But its story reveals how science evolves, not by discarding questions, but by refining them, replacing intuitive but flawed explanations with evidence. It shows how observation can mislead, and how only careful, repeated tests can reveal the hidden processes beneath appearances. Imagine again the farmer, the baker, the housewife of centuries past. To them, the sudden appearance of worms or flies seemed magical, even inevitable. To us, it is eggs, spores, microbes, all invisible to their eyes. What they called spontaneous, we call life's continuity. And yet, their curiosity, their attempt to explain the everyday miracle of life's persistence, connects us still. Phlogiston, the fire element. That wasn't. Strike a match and watch it burn. The flame leaps to life. Wood blackens, smoke curls upward, and heat pours into the air. For us, chemistry explains this with oxygen, combustion, and energy release. But for scientists of the 17th and 18th centuries, something far less visible seemed to be at work. Fire was not simply a process, but a substance, a hidden essence flowing out of matter. They called it phlogiston. The word comes from the Greek for burnt. In the late 1600s, German physician and alchemist Johann Joachim Becher proposed that combustible materials contained an oily, fire-like principle. His student Georg Ernst Stahl refined the idea into a full theory. According to Stahl, all flammable matter held phlogiston, and burning was the act of releasing it. A log in the fire, a candle's wick, even metals when heated, all glowed, smoked, and left behind ash because their phlogiston had escaped. The beauty of the theory was its simplicity. It explained why wood left ash. Ash was matter without phlogiston. It accounted for smoke rising. Phlogiston, light and airy, drifting into the atmosphere. Rusting of metals was also understood this way. Iron exposed to air gradually released its hidden phlogiston, leaving behind a dull, brittle residue. To the scientists of the day, the logic seemed unassailable. For decades, phlogiston guided experiments and textbooks across Europe. Chemistry was not yet the modern science of atoms and molecules, but a shifting field of alchemy, medicine, and metallurgy. Within that landscape, phlogiston was a unifying principle. It tied fire, heat, and decay together. Even plants seemed to fit the pattern when burned. They gave off flame and smoke, proof of phlogiston inside. And yet the theory carried contradictions from the start. If combustion was the loss of phlogiston, then substances that burned should weigh less afterward. But metals that rusted or were calcined in furnaces actually gained weight. Some phlogistonists explained this away by claiming phlogiston had negative weight, a kind of buoyant substance whose absence made matter heavier. Others argued that phlogiston was incredibly light, almost weightless, so the increase in weight came from matter absorbing other fluids while losing phlogiston. The patches grew complex, but the theory held sway. By the 18th century, chemists began to notice more cracks. Careful experiments showed gases playing a role in combustion. Candles burned out in sealed containers, not because phlogiston filled the space, but because something in the air was consumed. Still, belief in phlogiston remained strong, partly because it felt intuitive. Fire seemed like a substance. How else to explain its leap from one object to another? The turning point arrived with the work of Antoine Lavoisier in the late 1700s. Through meticulous experiments, Lavoisier demonstrated that burning consumed a component of air, what we now call oxygen, and that the weight gain in metals came from combining with this gas, not from losing phlogiston. His balance sheets of matter and air revealed conservation of mass in chemical reactions. With his clarity, phlogiston collapsed. The fall was dramatic. Within a few years, chemistry transformed. Phlogiston was discarded. Oxygen chemistry rose, and the modern language of elements and compounds emerged. Lavoisier's work is now considered the birth of modern chemistry. Looking back, phlogiston is both amusing and sobering. Amusing, because the idea of a substance with negative weight sounds absurd. Sobering, because it reminds us that even brilliant minds can cling to elegant but flawed frameworks. Phlogiston fit observations well enough until better measurements demanded a new explanation. The story reveals the rhythm of science. Hypotheses arise from what seems obvious, persist through patches and exceptions, and finally yield when evidence makes a leap unavoidable. The phlogiston era trained chemists to observe, weigh, and record carefully. Its collapse was not a failure, but a step, scaffolding for the revolution to come. And though forgotten in laboratories, phlogiston lingers as a metaphor. We speak of burned-out workers as if their phlogiston has drained away. We picture passion as a fire within. The language of flame, depletion, and hidden reserves echoes the old idea, proof that discarded theories never vanish completely. They slip into metaphor, shaping the way we think long after their scientific life has ended. Imagine again a candle guttering in a 17th century study, a chemist scribbling notes by its light. He believes phlogiston is escaping into the night air. He is wrong, yet his observations build the bridge to a truer science. Fire, once thought a substance, is now understood as a reaction. And the forgotten theory of phlogiston remains as a reminder: even error can illuminate if we are willing to let its light fade into something new. Vitalism, a special life force. In the 18th century, science was carving the world into mechanisms. The heart was studied as a pump, the lungs as bellows, the nerves as strings transmitting signals. Life, it seemed, could be explained piece by piece, as if the body were a clock whose workings could eventually all be known. Yet even as physiology advanced, a stubborn conviction persisted: machines alone could never explain life. There must be something more, a hidden spark animating matter into living form. This was the doctrine of vitalism. At its heart, vitalism held that living beings were fundamentally different from non-living matter. A special essence or force, invisible and irreducible, infused organisms. Without it, bodies were mere collections of parts. With it, they breathed, grew, healed, and reproduced. To many physicians and philosophers, this seemed obvious. A corpse contained the same organs as a living body, but the difference between them was vast. How could mechanics alone account for consciousness, for will, for the mysterious striving of life? The roots of vitalism stretched far back. Aristotle spoke of a soul, psyche, that distinguished living from non-living. In medieval medicine, this became the vital spirit carried in the blood, sustaining health. By the Enlightenment, with chemistry and physics ascendant, vitalism was recast as a scientific principle. Thinkers like Georg Ernst Stahl argued that a vital force guided organic processes beyond the reach of chemical analysis. Cells, tissues, and fluids obeyed physical laws. Yes, but only under the supervision of this animating principle. Vitalism wasn't just speculation. It carried practical consequences. One of its strongest claims was that organic compounds could only be produced by living organisms. Life force, many believed, was necessary to assemble the complex substances of flesh, bone, and plant tissue. No laboratory could ever manufacture them. This was known as the doctrine of vital force. For decades, the belief held sway. Then in 1828, the German chemist Friedrich Wöhler performed an experiment that shook the doctrine. While trying to synthesize ammonium cyanate, an inorganic salt, he accidentally created urea, a compound found in urine. Here was an organic compound, born not from a living body, but from a laboratory reaction. Wöhler's discovery was hailed as a death blow to vitalism. If urea could be made without life, perhaps all organic substances could. Yet vitalism did not vanish overnight. Many argued that Wöhler's urea was an exception, a fluke. Others shifted the vital force from chemistry to biology more broadly, claiming that while molecules might be made artificially, the organization of living systems still demanded something extra. As microscopes revealed the complexity of cells, vitalists pointed to their mysteries as proof of a guiding essence. The debate persisted well into the 19th and early 20th centuries. Some biologists clung to vitalism as a defense against reductionism, the idea that life could be fully explained by physics and chemistry. Others embraced mechanistic science, seeing vitalism as a romantic holdover. As experimental biology advanced, discovering enzymes, genes, and biochemical pathways, the domain of vitalism shrank further. By the mid-20th century, mainstream science had abandoned it. Life in the laboratory was increasingly understood as chemistry scaled upward. Still, the ghost of vitalism lingers. Even today, when DNA, proteins, and cellular machinery are mapped with exquisite precision, questions remain that echo the old doctrine. What is consciousness? How does subjective experience arise from neurons? Why does life strive, adapt, and seem purposeful when non-living matter does not? While scientists no longer invoke a vital force, the sense of mystery has not disappeared, it has simply migrated to new frontiers. Vitalism also survives in language and culture. We speak of life energy, of being full of vitality. Many traditional medicines still invoke concepts of chi, prana, or spirits, cultural cousins of the vital force. In holistic health movements, the notion of an animating energy persists, even if mainstream science rejects it. The intuition that life is more than the sum of parts remains deeply human. Why did vitalism endure so long? In part, because it protected a sense of awe. To reduce life to mechanics felt, to many, like stripping it of meaning. Vitalism offered a way to honor the uniqueness of the living without denying science. And in truth, the scientific worldview does not erase wonder. It relocates it. What once was attributed to vital force is now seen in the staggering complexity of genetic codes, molecular machines, and evolutionary webs. Imagine a physician in 1800 placing a hand on a patient's chest. The heartbeat beneath his palm is not just the pumping of blood, but, to him, evidence of a vital flame. He cannot imagine it extinguished except by death, nor imagined as the work of levers and valves. He is wrong in detail, but not in spirit. He senses, as we still do, that life carries a quality that resists full description, no matter how finely science dissects it. Vitalism, forgotten as doctrine, lives on as reminder. It shows how fiercely we defend the difference between alive and not alive, how reluctant we are to see ourselves as only chemistry. And it suggests something humbling. Every theory, however flawed, is part of the long conversation by which humanity tries to name the spark within. Miasma theory of disease. Step into a city street in the 19th century. The air is thick with odors, open sewers running along cobblestones, refuse piled high, smoke from coal fires drifting between narrow buildings. Illness, too, lingers everywhere. Cholera sweeps through crowded neighborhoods. Malaria plagues marshy outskirts. Fevers and dysentery stalk households. To physicians of the time, the link seems obvious. Foul air, stinking and corrupted, is the cause of disease. This was the miasma theory, the belief that sickness spread through bad air arising from decay and filth. The idea was not new. It traced back to ancient times, to Hippocrates and Galen, who described miasmata, noxious vapors rising from rotting matter, as sources of epidemics. The very word malaria comes from the Italian mala aria, or bad air, a name that tells the story. For centuries, the logic felt irrefutable. People who lived near swamps fell ill more often. Outbreaks flourished in dirty, crowded quarters where sewage was exposed to the open air. Odor and disease walked hand in hand. By the 18th and 19th centuries, miasma theory became the dominant public health doctrine. City planners and physicians alike believed that to fight epidemics, one had to fight smells. Ventilation, wide boulevards, and open green spaces were prescribed not only for beauty but for health. London, Paris, and New York redesigned neighborhoods to increase airflow, assuming that cleaner air meant healthier citizens. Sewers were built and trash cleared, not because germs were understood, but because stench was feared. Miasma theory shaped medicine too. Doctors prescribed moving to the countryside for cleaner air. They urged patients to avoid damp, dark places, to open windows, to burn incense or herbs that masked or neutralized odors. In India, during colonial times, British authorities believed cholera was spread through miasmas and focused on cleansing streets rather than contaminated water supplies. Even Florence Nightingale, the famed nurse of the Crimean War, subscribed to the miasma idea. She designed hospitals with large windows and airy wards, convinced that fresh air was the cure. To us, the theory seems crude, but it was not entirely without merit. Filthy, unsanitary conditions did correlate with disease outbreaks. Cleaning streets and improving sewage systems often reduced epidemics, not because miasma was real, but because germs were inadvertently being removed. Public health benefited, even under a mistaken framework. Miasma theory was wrong in mechanism, but right in motivating reforms that saved countless lives. Still, its flaws grew apparent as science advanced. The most famous challenge came from the cholera epidemics in London during the mid-1800s. The city reeked with foul smells, especially during the Great Stink of 1858, when the Thames River itself became a flowing sewer. To miasmatists, the stench was proof that disease swirled in the air. Yet physician John Snow suspected otherwise. Mapping cholera cases, he traced outbreaks to contaminated water pumps, not smelly air. When he persuaded authorities to remove the handle of the Broad Street pump, the epidemic subsided. His work suggested a waterborne cause, undermining miasma theory. The final blows came with Louis Pasteur's germ theory and Robert Koch's identification of specific bacteria causing tuberculosis and anthrax. Invisible microbes, not invisible vapors, spread disease. The foul smells of decay might accompany illness, but they were not its cause. By the late 19th century, the miasma doctrine was fading, replaced by microbiology's clearer lens. Yet miasma theory's shadow lingers. Even today we instinctively link odor with danger. A foul smell makes us recoil, our bodies primed to suspect contamination. The intuition that air can carry illness is not entirely wrong. After all, colds, influenza, and COVID-19 do travel in airborne droplets. What was mistaken was the nature of the agent, not the suspicion itself. The story of miasma reveals how science often advances wrong ideas can still lead to right actions. By chasing smells, cities built sewers, improved sanitation, and reduced crowding. They fought imaginary vapors but destroyed real breeding grounds for germs. Progress is rarely a clean break from ignorance. More often, it is a messy process where error paves the road to truth. Imagine once more that crowded city street, the stench rising with the summer heat. To its residents, disease truly was in the air. They lived in fear of every foul odor, masking their faces with handkerchiefs soaked in vinegar or herbs. They were wrong about the mechanism, but not about the risk. In their mistaken terror, they cleaned, they ventilated, they built, and in doing so they unknowingly prepared the ground for the germ theory that would replace their fears with knowledge. Caloric fluid, heat as invisible substance. Hold your hand near a fire and you feel warmth flow outward, almost as if something invisible is streaming from the flame into your skin. Step into a cold room, and it feels as though that same something has been drained away. For scientists of the 18th century, this sensation was more than metaphor. Heat, they believed, was not motion or energy but a subtle substance in its own right, an invisible material that moved from one body to another. They called it caloric. The caloric theory was elegant in its simplicity. Heat was imagined as a weightless, invisible fluid that filled matter. When a body was hot, it was because it contained a great deal of caloric. When it was cold, it held less. Like water poured from one vessel to another, caloric could flow from hot objects into cooler ones until equilibrium was reached. The idea gave form to something otherwise intangible, turning the experience of warmth into a phenomenon scientists could grasp and describe. The theory offered clear explanations for everyday events. Why does metal feel colder than wood at the same room temperature? Because metal allows caloric to flow more quickly out of your hand, draining it faster. Why does a kettle warm water? Because caloric flows from the fire into the pot, then into the liquid. Even melting and boiling were framed as transitions in caloric content. Enough caloric added to ice would unlock water, and more would transform it into vapor. Physicists like Antoine Lavoisier, who had already overthrown Phlogiston with his theory of oxygen, adopted caloric as the reigning model of heat. To him and his contemporaries, caloric explained expansion. Heat a gas, and its particles seemed to swell apart, not because of invisible motion, but because caloric wedged itself between them. Heat a metal rod, and it lengthened slightly as caloric forced its atoms to make room. Caloric even offered a way to think about fire itself. Combustion was not the release of energy, but the rapid liberation of caloric trapped inside materials. The flame was caloric escaping, rushing outward into the air. Once released, the substance could not be destroyed, only transferred. Conservation was a central feature of the theory. Caloric was eternal and indestructible, merely moving between objects. For a time, the caloric model worked surprisingly well. Engineers used it to improve steam engines. Early thermometers were calibrated as if they measured the amount of caloric in a body. The theory's logic seemed unassailable. If heat flowed like a fluid, then it could be quantified, conserved, and predicted. But cracks appeared as experiments grew more precise. In the late 1700s, Count Rumford Benjamin Thompson made a famous observation while overseeing the boring of cannons in Bavaria. Workers drilled metal barrels for hours, and the boring tools grew extremely hot. Rumford noted that the process produced seemingly endless heat. If caloric were a finite fluid stored in metal, the supply should eventually run out. Instead, as long as drilling continued, heat kept flowing. Rumford concluded that heat might not be a substance at all, but a form of motion generated by friction. Still, caloric was not immediately abandoned. Scientists clung to it, adding adjustments and refinements. They argued that friction merely released caloric faster, or that the substance was stored in ways not yet understood. But more experiments piled up. In the early 19th century, James Prescott Joule's careful studies of mechanical work and heat showed that motion could consistently produce heat, and that there was a fixed relationship between the two. This discovery, the mechanical equivalent of heat, pointed toward a new understanding: heat as energy, not substance. By the mid-1800s, the caloric theory gave way to the kinetic theory of heat. Instead of fluid slipping between atoms, heat was explained as the jostling motion of particles. Temperature measured the average speed of atoms, and thermal energy was simply energy of motion. Caloric vanished from textbooks, replaced by the modern science of thermodynamics. Yet the ghost of caloric lingers in our language. We still talk about flowing heat as though it were a substance moving between objects. We describe warmth being lost or gained. Even the word calorie, used to measure food energy, recalls the old doctrine. The metaphor of heat as something that can be transferred like fluid remains useful, even though we know it is motion, not matter, that animates warmth. The story of caloric teaches us how even wrong theories can advance knowledge. By treating heat as a conserved substance, scientists developed tools for measuring and predicting thermal processes. They built engines, refined instruments, and collected data. When the theory collapsed, those data became the foundation for thermodynamics, one of the most powerful frameworks in science. Error was not wasted. It was scaffolding for discovery. Imagine again holding your hand to the fire. To us, warmth is energy carried by invisible molecules, vibrating and colliding. To Lavoisier and his peers, it was caloric streaming out, an invisible tide filling your skin. They were wrong, but their wrongness led to insight. The forgotten fluid dissolved, but in its place rose the laws of energy conservation, engines that powered industry, and a deeper understanding of the restless dance of atoms. Luminiferous ether, medium of light. Stand in an open field at night. The stars gleam across unimaginable distances, their light falling gently into your eyes. For most of history, such a wonder carried with it a profound question. How does light travel through the emptiness of space? Sound needs air. Ripples need water. Vibrations need a medium. Could light simply leap across a void without support? To many scientists, that seemed impossible, and so they imagined an invisible substance filling all of space, a cosmic medium through which light moved. They called it the luminiferous ether. The idea of ether has ancient roots. Aristotle described it as the fifth element, different from earth, air, fire, and water, a divine substance filling the heavens and ensuring the perfection of celestial motions. Centuries later, as optics and physics developed, the ether took on a new role, not a mystical quintessence but a physical medium, thinner than air yet pervasive, elastic and necessary for the transmission of light. By the 17th and 18th centuries, debates raged about the nature of light. Isaac Newton favored a particle theory, tiny corpuscles emitted from luminous bodies. Christian Huygens, in contrast, argued that light was a wave spreading through a medium as ripples spread through water. If Huygens was right, then space could not be empty. Waves needed something to wave in. The ether became the solution, invisible yet universal, subtle enough to fill glass, stone, and the cosmic void alike. In the 19th century, the ether gained sophistication. Physicists described it as perfectly transparent, weightless, frictionless, yet rigid enough to carry the incredibly fast vibrations of light. It had to be strong to transmit such rapid oscillations, but delicate enough to offer no resistance to planets moving through it. This balancing act made the ether a paradoxical substance, endowed with contradictory properties to preserve the theory. Still, it persisted. Without it, waves of light seemed unthinkable. Experiments were devised to probe the ether. If Earth moved through this cosmic medium, then the speed of light should vary depending on our direction of travel. Like a swimmer in a current, light should move faster with the flow and slower against it. In 1887, Albert Michelson and Edward Morley built a sensitive interferometer to detect this ether wind. Their results shocked the scientific world. They found no difference. Light speed was constant in all directions. The ether wind, if it existed, could not be felt. The failure of the Michelson-Morley experiment was devastating. If the ether was real, why did careful measurement show nothing? Physicists tried to save the theory by proposing strange fixes. Some suggested the ether was dragged along by Earth, nullifying the wind. Others argued that moving objects physically contracted in the direction of motion, masking the effect. These patches, ingenious but desperate, were the epicycles of 19th-century physics layered onto a weakening framework. Then came Albert Einstein. In 1905, his special theory of relativity swept the ether aside. Light, he proposed, did not need a medium. Its speed was a universal constant, woven into the structure of space-time itself. The transformations of length and time were not quirks of an undetectable medium, but fundamental aspects of reality. The ether, once essential, dissolved like mist under a rising sun. The death of the ether was more than the end of a theory. It was a turning point in physics. It forced scientists to accept that not all waves require a medium, that emptiness could carry its own properties. Space was no longer filled with invisible fluid, but endowed with geometry, capable of bending and stretching under mass and energy. What replaced the ether was stranger and richer than what it had been invented to explain. Yet the legacy of the ether endures. It taught scientists to take the wave nature of light seriously. It inspired generations of experiments, sharpened instruments, and paved the way for relativity. Even today, echoes of the idea return in new guises: quantum fields filling space, vacuum energy bubbling with virtual particles. In modern physics, the void is never truly empty. While the luminiferous ether is gone, the intuition that space itself carries hidden structure has not been abandoned. Imagine again the night sky. For centuries, thinkers believed a delicate fabric stretched between every star, a silent ocean through which light swam to reach your eyes. They were wrong about its nature, but not about the wonder. The ether was a placeholder, an attempt to make sense of the impossible fact that starlight crosses darkness. In forgetting it, we remember something else, that theories are bridges, not destinations, and even vanished bridges once carried us closer to truth. Preformationism, tiny humans in sperm. Open a microscope slide in the 17th century and peer through one of the earliest lenses. What you see is blurry, distorted, but extraordinary. Inside a droplet of semen, or so it seemed to early observers, was the outline of something uncanny, a tiny, curled-up figure, complete with head, arms, and legs. It was not a vague blob of potential, but a miniature human, waiting to unfold. This was preformationism, the belief that every organism began its life already fully formed, only needing growth to reach adult size. The theory was a natural attempt to answer an ancient question: where do new beings come from? To preformationists, the answer was simple. There was no mysterious process of assembly, no gradual construction of body parts. Instead, all the complexity was already present in miniature. A newborn child was once a tiny homunculus, folded into the reproductive cells of its parents. Development was not creation, but expansion. There were two main schools of preformation. The spermists believed that the homunculus resided in the sperm cell. Each sperm contained an entire miniature human, which once placed in the womb, simply grew. The ovists, on the other hand, argued that the miniature human was housed in the egg. The sperm merely activated its growth, like striking a match to ignite fuel. Whichever side one took, the core conviction was the same: the form of life already existed, fully prepared from the very start. To modernize, preformationism is almost whimsical. The image of millions of tiny people swimming inside every drop of semen or hidden within every egg seems absurd. Yet it had an intuitive appeal. Look at an acorn. Does it not already seem like a tiny oak waiting to grow? Look at a chick emerging from an egg. Does it not appear as though it was always hidden there, merely getting larger? Preformation promised to eliminate the mystery of development by replacing it with a simple metaphor of unfolding. The theory also fit comfortably with prevailing philosophies and religious views. If every new organism already existed in miniature, then the entire future of the human race had been packed into the first creation. Eve's ovaries, according to ovists, might have contained every generation to come, nested like Russian dolls within one another. This satisfied theological concerns about divine foreknowledge and the fixity of life. Nothing new ever truly appeared. It was all present from the beginning, waiting its turn. But preformation carried strange implications. If every future generation was preformed inside the reproductive cells of the first humans, then the number of nested homunculi was practically infinite. Within Adam or Eve resided not just their children, but their grandchildren, great-grandchildren, and countless more, each folded smaller and smaller, a chain stretching across all time. Philosophers called this idea emboîtement, or infinite encasement. For some, it was a sign of divine design. For others, it was a troubling paradox. Despite its oddities, Preformation had scientific defenders. The Dutch microscopist Antony van Leeuwenhoek, famed for discovering bacteria and sperm cells, described what he believed were tiny men inside sperm. His drawings suggested detailed little bodies, though we now know they were artifacts of imagination and poor optics. Others published illustrations of homunculi, earnest attempts to reveal life's secret. The microscope, still new and mysterious, lent authority to these interpretations. Yet not everyone was convinced. The rival theory of epigenesis, championed by thinkers like William Harvey, argued that organisms developed gradually from unorganized matter, with structures emerging stage by stage. To Harvey, all animals come from an egg, and the process was one of differentiation, not mere unfolding. For centuries, the debate between preformationists and epigeneticists divided natural philosophers. By the 18th century, advances in embryology began to undermine preformation. Careful observations of chick embryos showed structures appearing progressively, not revealed all at once. The microscope improved, showing cells dividing and differentiating rather than tiny bodies waiting in suspension. In the 19th century, cell theory and experimental embryology finally buried preformation. The discovery of DNA in the 20th century confirmed it beyond doubt. Life unfolds not from miniature copies, but from coded instructions guiding growth. Why then did preformation persist so long? Because it offered certainty in a field clouded by mystery. To explain development as unfolding was easier than wrestling with the complex, invisible processes that we now know involve genetics, biochemistry, and cellular choreography. It was, in a sense, a comforting story. Life as a series of boxes opened in sequence rather than as an unpredictable emergence from invisible seeds. And though discarded as science, preformation lingers as metaphor. We still speak of potential as though it were already present, the artist hidden in the child, the oak inside the acorn. We imagine futures folded into the present, waiting only to grow. The homunculus has vanished from biology, but survives in language, in the way we describe possibility as something latent, preformed within us. Picture again the early microscopist peering into his crude lens. He thinks he sees a tiny person curled in a cell, a universe of futures contained in one drop. He is wrong, but not foolish. He is grappling with the same awe we feel when considering how a single cell becomes a being. His mistake was not in asking the question, but in answering too quickly with a story that was vivid, simple, and false. Preformation is forgotten in laboratories, yet it marks a step in our attempt to understand life. It shows how imagination fills gaps when evidence runs thin, and how even false images can carry us forward until better ones replace them. Today we know embryos are not tiny people waiting to grow, but intricate symphonies of development, coded and conducted by invisible instructions. And yet, the wonder remains: from a cell, a person, from almost nothing, everything. Lamarckism, inheritance of acquired traits. Imagine a blacksmith in the 18th century, his arms thickened by years of swinging the hammer. Each strike hardens his muscles, and each callus tells the story of his trade. Now picture his children, born strong with broad chests and hardy frames, already carrying the imprint of their father's labor. This was not just poetic imagination, but for many, a scientific conviction. Traits acquired during life could be passed directly to offspring. Work, effort, and habit did not vanish with death. They were inherited. This was Lamarckism, the theory of acquired characteristics, one of the most influential forgotten ideas in biology. The doctrine is named for Jean-Baptiste Lamarck, a French naturalist who lived during the turbulent years of the late 18th and early 19th centuries. Lamarck began his career in botany and later turned to zoology, studying the immense diversity of animals. At a time when many believed species were fixed and unchanging, Lamarck dared to suggest otherwise. Species evolved. They adapted, transformed, and produced new forms. For this bold claim, he is remembered as one of the earliest evolutionary thinkers. But Lamarck's explanation for how evolution occurred was very different from Darwin's later theory. He proposed two main principles. The first was the use and disuse of organs. Structures that were exercised and used frequently would grow stronger and more developed. Those that were neglected would shrink and disappear. The second principle was inheritance of acquired traits. Changes that an organism experienced during its life, through habit or environment, would be passed on to its offspring. The most famous example is the giraffe. Lamarck imagined ancestral giraffes as antelope-like animals that stretched their necks to reach leaves higher in the trees. Over generations, this stretching lengthened their necks, and the acquired length was inherited. Bit by bit, the modern giraffe emerged. Similarly, the blacksmith's muscular arms, or the scholar's sharp mind honed by study, could be bequeathed to their children. Effort, habit, and experience became the engines of evolution. In its time, Lamarckism felt logical. It matched observations. Muscles do grow with use, and disuse does cause atrophy. Animals in new environments do change their habits. And the idea that one generation's struggles could ease the path of the next carried a certain justice. It fit a world in which progress seemed possible, not just for individuals, but for entire species. For decades, Lamarck's theory found believers. It resonated with a culture fascinated by self-improvement and the power of habit. It also offered a hopeful narrative. What we do matters not only for ourselves, but for our descendants. Hardship endured today might yield strength tomorrow. In contrast, laziness or neglect could doom a lineage. The moral overtones of the theory made it attractive, especially in the 19th century. But cracks appeared. Naturalists struggled to find clear evidence that acquired traits really were inherited. A scar on a parent did not mark the child. Muscles strengthened by labor did not automatically appear in offspring. Darwin's theory of natural selection, published in 1859, provided a different explanation. Traits varied naturally, and those best suited to survival were passed on, not because they were earned, but because they gave advantage. Evolution was not a reward for effort, but the consequence of differential survival. Even Darwin, however, was not entirely free of Lamarckian influence. He speculated about pangenesis, a mechanism in which particles from all parts of the body might influence reproductive cells. It was only with the rise of modern genetics, beginning with Gregor Mendel's experiments and culminating in the discovery of DNA, that Lamarck's model truly collapsed. Inheritance followed fixed rules. Traits arose from genetic variation, not from acquired habits. The blacksmith's arms were his alone. And yet, Lamarckism has never fully vanished. In the 20th century, some Soviet biologists under Trofim Lysenko revived a Lamarckian vision, insisting that crops could be trained to endure harsh conditions and pass those adaptations to their seeds. Lysenkoism, politically enforced, set back Soviet agriculture disastrously. In the West, mainstream biology dismissed Lamarckism as a cautionary tale of ideology masquerading as science. But in recent years, whispers of Lamarck have returned in a new form. The study of epigenetics, chemical modifications to DNA that affect gene expression, suggests that environment and experience can indeed influence inheritance, at least to a degree. For example, stress or diet in one generation can alter patterns of gene activation in the next. While not a revival of Lamarck's theory in its pure form, epigenetics has reopened discussion about how life experience might echo across generations. Why does Lamarckism linger in imagination? Perhaps because it flatters our sense of agency. It promises that our choices leave marks deeper than memory, that what we practice, endure, or cultivate may ripple forward into the future. Darwin's natural selection feels impersonal, a grand sieve indifferent to human striving. Lamarck's theory, by contrast, tells a story of effort rewarded, of hard work carved into the flesh of descendants. Imagine Lamarck himself pacing through Paris as revolutions reshape society. He sees the world in flux, believes in progress, and carries that vision into biology. Species like nations could advance. Habits could change destiny. His theory was wrong in detail, but not in its spirit of daring to see life as dynamic, not fixed. Today we smile at the notion of tiny humans tucked in sperm or acquired traits passed like heirlooms. But we also recognize the courage of those who sought answers before the right tools existed. Lamarckism is forgotten as doctrine but remembered as a step, an earnest attempt to explain the mysterious continuity between generations. It shows how science evolves, not by leaps from ignorance to truth, but by a slow procession of ideas, each partly wrong, each strangely necessary. Maternal impression, thoughts, shape babies. For most of human history, pregnancy was a realm of mystery, awe, and fear. Without knowledge of genetics or embryology, people sought patterns in birth, trying to explain why some children resembled their parents while others did not, why deformities appeared suddenly, or why birthmarks seemed strange and symbolic. One theory, passed down through centuries of folklore and medicine, claimed that a mother's thoughts, fears, and experiences during pregnancy could physically shape her unborn child. This was the doctrine of maternal impression. The logic was simple, even intuitive. If a pregnant woman was startled by a sudden sight, the shock could imprint itself on the fetus. If she gazed too long at a particular image, the likeness might be etched into the baby's body. Cravings, emotions, traumas, all could be inscribed directly into the developing child. A red birthmark might be explained by the mother's longing for strawberries. A clubfoot might be traced to her having seen a lame beggar. A hare lip could be blamed on a pregnant woman's fright at the sudden leap of a rabbit. Such stories abounded in antiquity and the Middle Ages. Physicians like Hippocrates and Galen mentioned maternal influences, though they lacked details. In Renaissance Europe, the belief flourished, mixing with superstition. Midwives warned expectant mothers to avoid disturbing sights, to keep calm, and to resist cravings, lest their emotions leave physical scars on their children. Pregnant women were sometimes shielded from upsetting scenes, as if their gaze itself could wound the unborn. In the 17th and 18th centuries, maternal impression was even invoked in legal and moral debates. If a child was born with deformities, blame could be directed at the mother's imagination or her behavior during pregnancy. In some cases, it was used to accuse women of witchcraft, suggesting that their unnatural thoughts had cursed their offspring. The theory gave society a way to explain anomalies, but it also burdened women with guilt for tragedies beyond their control. Doctors recorded case after case, convinced of its truth. A child with a birthmark shaped like a fruit must be proof of maternal craving. A child born with extra fingers or toes must have been marked by something the mother had seen or feared. In an age without microscopes or chromosomes, such explanations filled the gap. They were stories dressed as science, providing meaning where knowledge was absent. The appeal of maternal impression was not only medical but symbolic. It reinforced the belief that mothers carried a mystical responsibility for shaping life, that their inner worlds leaked into the physical form of their children. It made pregnancy a sacred but perilous time, when the mind's wanderings might become destiny. In a way, it reflected the deep intuition that environment and emotion matter in development, though the mechanism imagined was fantastical. The theory persisted well into the 19th century, despite growing advances in anatomy and biology. But as embryology matured, cracks appeared. Careful studies showed that malformations arose from disruptions in early development, not from a mother's fleeting thoughts. Birthmarks were the result of blood vessel growth, not strawberry cravings. Inheritance followed patterns that maternal impression could not explain. Still, the idea lingered, woven into culture long after science moved on. Today, maternal impression is regarded as a relic, a forgotten theory alongside phlogiston and miasma. Yet its echoes remain. Parents still joke about cravings influencing babies. Pregnant women are still told to avoid stress, and while not because of birthmarks, we now know that maternal stress hormones can influence fetal development. The intuition that a mother's experience matters for her child's future was not entirely false, it was only misinterpreted and overstated. In a modern key, maternal impression finds a curious afterlife in epigenetics. Though not caused by sudden sights or cravings, a mother's environment, diet, stress, exposure to toxins can alter how genes are expressed in her child. These changes do not rewrite DNA, but they do shape development in subtle ways. Here at last, science gives a mechanism for what older generations sense that mothers' lives leave imprints on their children, though not in the literal or fantastical ways once imagined. Why did maternal impression survive for so long? Because it fit the human hunger for meaning. A child born different was not an accident, but a sign, a message, a traceable story. It gave parents a narrative, even if it was wrong. In the face of uncertainty, stories feel kinder than silence. Imagine a woman in the 17th century, frightened by a barking dog in the street. Months later, her baby is born with a birthmark. Neighbors nod, certain they know the cause. She may carry guilt, or perhaps reassurance. Her child's difference has an explanation. It is not chance, not mystery, but the visible echo of a moment. The theory may be forgotten, but the desire to explain, to connect inner life with outer form, has never gone away. Polygenism, separate human origins. Walk into a lecture hall in the 18th century, and you might hear a debate that sounds unsettling to modern ears. Where did humanity begin? Were all people descended from a single pair, as religious tradition insisted? Or did different human groups arise separately, in different parts of the world, each with its own origin story? This second idea was known as Polygenism, the belief that human races had multiple, independent beginnings. Polygenism emerged in an age of exploration and empire, when European scholars encountered people from Africa, the Americas, Asia, and the Pacific, whose appearances, languages, and cultures seemed vastly different from their own. The sheer diversity of humanity raised questions. Could all this variety have sprung from a single source, as monogenists claimed, or was it more plausible that different groups were created separately, each tailored to its environment? At first glance, polygenism carried a veneer of scientific neutrality. Observers pointed to differences in skin color, hair texture, skull shape, and stature, treating them as evidence of separate origins. Some naturalists, influenced by the methods of taxonomy, categorized human beings as if they were distinct species. Others used the ancient idea of climate shaping body and temperament, but concluded that climate alone could not explain the depth of variation they saw. Polygenism seemed, to them, like a straightforward answer. But the theory was never merely about biology. It quickly became entangled with politics, religion, and morality. In Europe and America, polygenism was often invoked to justify slavery and colonial domination. If different races had different origins, then perhaps they were not truly one family. Perhaps they were unequal in capacity, in rights, even in humanity itself. Pseudo-scientific arguments flourished, cloaked in the language of natural history, but driven by social agendas. The most notorious expression came in the 19th century with writers like Samuel George Morton, who collected skulls and measured cranial capacity, claiming to find innate differences between races. His work, and that of others, fed into scientific racism, reinforcing hierarchies that aligned conveniently with colonial power. Polygenism, under this guise, was not just a forgotten scientific theory, but a weapon used to rationalize oppression. Yet not all polygenists framed their arguments so harshly. Some, genuinely puzzled by human diversity, argued that separate origins did not mean inequality. They suggested that multiple creations could coexist with dignity, that humanity was a tapestry woven from different threads. Still, the dominant cultural currents made polygenism less a neutral hypothesis than a justification for prejudice. Monogenism, by contrast, insisted on a single origin. For religious thinkers, this aligned with the story of Adam and Eve, a shared ancestry under God. For abolitionists, it supported the idea of universal brotherhood. Science gradually shifted in this direction, especially with Charles Darwin's theory of evolution. Darwin argued that all humans shared common ancestors, that differences were variations shaped by natural and sexual selection, not evidence of separate creations. Modern genetics has confirmed this, showing how closely related all humans are, regardless of outward diversity. Why, then, did polygenism persist for so long? Partly because it offered a convenient explanation for difference at a time when tools for studying heredity were limited. It also appealed to human tendencies toward division, the instinct to see groups as fundamentally separate. And in a more subtle way, it reflects the broader struggle of science to disentangle itself from social and political forces. Theories are not born in isolation. They emerge within cultures that reward some explanations and resist others. Today, polygenism is scientifically discredited. We know that humanity arose in Africa, that genetic diversity is greatest there, and that all other populations descend from migrations outward. The differences between groups are superficial, a handful of genetic variations compared to the overwhelming sameness of our DNA. Modern science tells us not only that we share one origin, but that we are far more alike than different. And yet the shadow of polygenism lingers, though no longer couched in scientific terms. The temptation to treat groups as separate, to imagine hard boundaries between us and them, remains powerful. The forgotten theory reminds us how easily science can be misused when it drifts into the service of prejudice. Imagine again that 18th century lecture hall. A scholar stands at the podium, pointing to skulls and specimens, convinced that humanity's variety proves separate beginnings. His certainty feels rational to him, supported by evidence he misreads. But outside, in the crowded streets, people of different origins meet, trade, marry, and build lives together. Reality itself defies his theory. Polygenism is forgotten now as a scientific claim, but it endures as a cautionary tale. It shows how the desire to explain difference can be bent into division, and how knowledge without humility can become a tool for harm. It reminds us that the story of human origins is not many but one, and that our true challenge is not to prove our separateness, but to remember our kinship. Trepanation as universal cure. Imagine a stone tool held against a human skull, then struck or twisted until a neat circle of bone is removed. The patient is alive, conscious, and astonishingly sometimes survives. This practice, known as trepanation, is one of the oldest surgical procedures in human history. Archaeologists have found skulls from as far back as 7,000 years ago across Europe, South America, Africa, and Asia, each bearing round or rectangular holes carefully carved into bone. The remarkable part is not only the scale of the practice, but the evidence of healing, edges of bone smoothed over, proof that people lived long after the procedure. Why was trepanation performed? In the absence of germ theory, neurology, or modern medicine, cultures explained illness and suffering through spirits, pressures, and imbalances. Trepanation seemed to offer a universal cure. For headaches, seizures, and mental distress, a hole in the skull could release the demon, spirit, or trapped force. For head injuries in battle, it might relieve pressure or bleeding. In some traditions, it was even performed for spiritual reasons, to open the mind to visions or to connect with the divine. The practice spread across continents, which suggests more than accident. In Neolithic Europe, skulls with trepanation marks have been unearthed in France and Ukraine. In the Andean cultures of South America, trepanation was highly developed, with surgeons using obsidian blades to treat warriors injured in conflict. In Africa, records from the 19th century describe similar practices continuing among certain tribes with surprisingly high survival rates. The idea in one form or another was nearly universal: when in doubt, open the skull. From a modern perspective, the logic seems both horrifying and oddly prescient. Horrifying because without anesthesia or sterile tools, the pain and risk of infection must have been immense. Oddly prescient because relieving intracranial pressure by drilling into the skull is in fact a valid neurosurgical procedure. Modern medicine uses trepanation's descendant, craniotomy, to treat hematomas, tumors, and swelling. What Neolithic healers discovered by trial and error survives in principle today, though with vastly improved tools and knowledge. In the Middle Ages, trepanation persisted in Europe, often framed by the theory of the four humors. A blow to the head might disturb the balance of fluids. Opening the skull could release the bad humors. Physicians recommended it for head injuries, epilepsy, melancholy, even to release spirits thought to cause madness. The surgeon's kit included specialized instruments, trepananes, circular saws designed to cut bone with precision. To them, this was not crude but refined medicine. The Renaissance brought new anatomical knowledge, but trepanation remained common. Ambroise Paré, the famous French surgeon, described techniques for drilling the skull to treat fractures or relieve pressure. Survival rates improved as surgical skill advanced, though infection still killed many. Over time, as other treatments became available and the causes of disease were better understood, trepanation's reputation as a cure-all declined. Yet it never disappeared entirely. By the 19th and 20th centuries, trepanation lingered on the edges of medicine and mysticism. Some fringe advocates claimed that drilling a hole in the skull could expand consciousness, increase blood flow to the brain, or restore childlike clarity. A few daring individuals even performed it on themselves, convinced they would gain heightened awareness. These eccentric revivals, though medically discredited, show how enduring the idea of opening the head as liberation remains. Why did trepanation last so long across so many cultures? Partly because in some cases it worked. Patients with head trauma might have survived longer if pressure was relieved. In other cases, the placebo effect or cultural faith in the procedure may have eased suffering. Above all, it offered an explanation and an action in the face of illness. When people are desperate, doing something, no matter how risky, feels better than doing nothing. Today, trepanation belongs to the catalog of forgotten theories and practices, yet it is not entirely irrelevant. It reminds us that medical knowledge grows slowly, often built on trial, error, and courage. Early healers had no microscopes, but they had sharp eyes, steady hands, and the will to act. Their patients, too, had courage unimaginable to us, enduring unimaginable pain in hope of relief. Picture a skull with its careful round window cut into bone. To us, it is an artifact, a relic of primitive medicine. To the people of the time, it was hope, treatment, ritual, even salvation. Trepanation is both a monument to ignorance and a testament to resilience. It shows how humans have always tried to wrestle with suffering, even when their theories were wrong. And it leaves us with a strange continuity. The tools have changed, but the impulse remains the same, to reach inside the hidden chambers of the body in search of healing, even at the risk of opening the skull itself. Bloodletting for every illness. For much of recorded history, if you were ill, no matter the complaint, the physician's answer was likely the same: open a vein. From headaches to fevers, from melancholy to infection, from plague to simple fatigue, the cure was thought to lie in draining the body of its most vital fluid. This was the practice of bloodletting, one of the longest-lasting treatments in medical history, applied for more than 2,000 years and across nearly every culture. The origins of bloodletting are deeply tied to the ancient theory of the four humors: blood, phlegm, yellow bile, and black bile. Health physicians believed was a matter of balance. If a patient had too much blood, a state called plethora, the excess had to be removed. Too much vigor meant fever, inflammation, or mania. The cure was simple: release the surplus until harmony returned. Bloodletting became the physical ritual that made the theory tangible, a way to act directly on invisible imbalances. Methods varied. In Greece and Rome, physicians used knives or lancets to open veins in the arm or leg. In medieval Europe, barbers doubled as surgeons, offering haircuts and bloodletting in the same shop. Leeching was another common method. Jars of wriggling leeches were pressed onto the skin, their steady suction drawing out blood without the violence of blades. By the 18th century, leech therapy was so popular in France that millions were imported each year, their numbers dwindling from overuse. Bloodletting became an almost universal prescription. A fever, let blood. Chest pain, let blood. A troubled mind, let blood. The practice was so pervasive that refusing it seemed irresponsible. Patients themselves sometimes demanded it, convinced it was the only remedy. It carried symbolic power too. Illness was excess, and the cure was release. Watching dark blood stream from a vein made disease visible and treatment concrete. But behind its popularity lay tragedy. Excessive bloodletting often weakened patients fatally. During the Middle Ages, it was used during epidemics of plague, draining strength from people already near death. In the 18th century, it was the standard treatment for pneumonia, cholera, and even childbirth complications. George Washington, America's first president, suffered a throat infection in 1799. His doctors bled him repeatedly over 2 days, removing an estimated 5 pints of blood. He died, perhaps hastened not by illness alone, but by the cure. Why did bloodletting endure despite its dangers? Because sometimes, by coincidence, it seemed to help. A patient with high blood pressure might feel temporary relief after blood loss. Someone with a swollen joint might improve as the body adjusted to shock. And when patients recovered naturally, bloodletting was credited as the cause. Failures were blamed on too little blood having been removed, or on the illness being beyond cure. In this way, the practice insulated itself against contradiction. It also persisted because it gave doctors a role. Medicine in pre-modern times often lacked reliable tools. Bloodletting allowed physicians to act decisively, to demonstrate skill and authority. It reassured both patient and practitioner that something concrete was being done. In times of desperation, doing something was preferable to doing nothing. Resistance grew slowly. By the late 18th century, some doctors began questioning the wisdom of such aggressive treatments. Pierre Louis, a French physician, studied pneumonia patients and found no benefit from repeated bleedings. Data for one of the first times in medicine began to challenge tradition. Still, bloodletting did not vanish overnight. Well into the 19th century, it was taught in medical schools and practiced in rural clinics. Only with the rise of germ theory, antibiotics, and modern physiology did the practice finally fade from mainstream medicine. Yet it never disappeared entirely. Today, in carefully controlled forms, bloodletting survives as therapeutic phlebotomy for specific conditions such as hemochromatosis, where excess iron in the blood must be reduced, or polycythemia vera, where too many red cells cause dangerous thickening. In these narrow cases, the old ritual has been reborn as precise therapy, guided by lab tests rather than humoral philosophy. Bloodletting's story is not only one of error, but of persistence and symbolism. It shows how strongly culture, tradition, and intuition can hold a practice in place, even when evidence points elsewhere. It also illustrates a paradox of medicine. Patients often find comfort in visible acts, even when invisible truths would serve them better. The flow of blood gave illness a form, made healing seem tangible, even when it drained life instead of saving it. Imagine again a dim chamber centuries ago. A patient lies weak with fever. A physician enters carrying a brass bowl and a sharpened lancet. The family watches anxiously as blood streams into the bowl, convinced relief is on its way. Perhaps the patient recovers, perhaps not. But the ritual feels powerful, the gesture ancient. In their eyes, the doctor has drawn sickness itself from the body. Forgotten now as universal cure, bloodletting remains a haunting emblem of medicine's long struggle. It is a reminder that science grows not only by discovering truths, but by unlearning errors, that certainty is fragile, and that even the most respected treatments can one day be recognized as shadows. And yet from those shadows, modern medicine rose, replacing bowls and leeches with microscopes and molecules, still driven by the same human desire to lift suffering by whatever means we can. Spontaneous combustion of humans. In the dim firelit parlors of the 18th and 19th centuries, newspapers sometimes carried reports so strange they seemed to belong to ghost stories. A body, discovered reduced to ash, sat in a chair that remained largely untouched. Limbs were gone, organs destroyed, yet the room around was hardly scorched. The conclusion was chilling. Human beings, under mysterious conditions, could ignite and burn from within. This was the forgotten theory of spontaneous human combustion. The idea held that a person might suddenly burst into flame without any external spark. Victims were often described as elderly women. Alone, their remains discovered as piles of ash with only fragments of bone or a foot surviving. The mystery was sharpened by the lack of damage to nearby furniture. If a fire had consumed them, why had the room itself been spared? Writers seized on the phenomenon. In 1763, the case of Countess Cornelia Bandi of Italy was widely circulated, her body found in her bedroom, reduced almost entirely to ash, though her straw mattress was only lightly singed. Later reports added more such tales, each with lurid detail. By the early 19th century, spontaneous combustion had entered popular culture. Charles Dickens used it dramatically in his novel Bleak House, where the drunken rag merchant Krook dies by bursting into flame. Explanations varied. Some blamed alcohol, suggesting that heavy drinking saturated the body with flammable spirit, turning flesh into fuel. Others pointed to divine punishment, the fire of judgment manifesting on earth. More naturalistic thinkers argued that internal gases or bodily oils might, under rare conditions, combust on their own. With limited forensic science, the leap to supernatural fire seemed less absurd than it does now. To the public imagination, spontaneous combustion carried a symbolic weight. Fire has long been a metaphor for passion, wrath, or spirit. To think the body might ignite from within was to believe that hidden forces, moral or chemical, smoldered inside us. It was both horrifying and strangely poetic, the human form undone by its own unseen flame. Skeptics, however, began to investigate. In the 19th century, experiments suggested that the so-called victims may have fallen prey to more ordinary fires, aided by what came to be called the wick effect. A small flame from a dropped candle or ember could ignite clothing. Human fat, once heated, could liquefy and be absorbed by fabric, turning the body into its own fuel source. Like a candle wick drawing wax, the smoldering continued slowly, reducing flesh to ash while leaving much of the room intact. This explanation, while grisly, fit the evidence better. Most reported cases involved elderly or infirm individuals near open flames, often alone. Alcohol might have made them careless or unconscious, though not flammable in itself. Once the slow burn began, hours of smoldering could consume the body, explaining the strange remains without invoking supernatural fire. Still, the legend of spontaneous combustion endured. Newspapers continued to sensationalize cases. Medical journals occasionally speculated about unusual metabolic processes or chemical reactions. For the public, the image of a person consumed by inner fire was too striking to abandon. It spoke to fears of the body's fragility, the suddenness of death, and the mystery of hidden forces. By the 20th century, science had largely closed the book. Controlled experiments with animal fat and cloth confirmed the wick effect. Forensic investigations of supposed cases almost always found external ignition sources. Spontaneous human combustion faded into folklore alongside other curious but discredited beliefs. Yet it still lingers on the margins, in tabloid stories, horror films, and whispered conversations about the strange and unexplained. Why did it fascinate for so long? Perhaps because it collapsed two anxieties into one, the fear of fire and the fear of the body betraying itself. Fire is one of humanity's oldest allies and enemies. To imagine it lurking inside us, waiting to erupt, is to feel that our own nature might turn against us. The theory also carried moral undertones. Victims were often portrayed as drunkards or sinners, as though their combustion were divine punishment. Science dismissed such claims, but society found in them a way to moralize death. Imagine again a quiet parlor, an armchair, a small fire in the grate. Morning comes, and a figure is gone, replaced by ash. Neighbors whisper of hidden flames, of bodies betraying themselves, of sins catching fire from within. They cannot know of fat wicking through cloth, of embers smoldering unseen. They tell the story as wonder, as warning, as mystery. Spontaneous human combustion is forgotten now as science, but not as image. It reminds us how mystery feeds imagination, how gaps in knowledge invite stories, and how even error can reveal our deepest fears. The truth is less supernatural but no less haunting. We are fragile, and in a careless moment, fire needs little help to claim us. Hollow Earth theories. Beneath our feet lies a mystery we rarely stop to imagine. We dig mines, drill wells, and bore tunnels, but compared to Earth's size, these are scratches on an eggshell. For most of human history, what lay beneath was a place of myth and speculation, an underworld of spirits, fires, or lost realms. Out of that mystery grew a scientific-sounding belief that captivated minds for centuries, the idea that Earth itself was hollow. The earliest forms of this idea were mythic. Ancient culture spoke of vast caverns where gods or the dead resided. The Greeks imagined Hades below, the Norse a dark underworld of hell, the Tibetans secret tunnels linking hidden kingdoms. As natural philosophy developed, these myths merged with speculation about Earth's structure. What if the underworld was not just spiritual, but physical? What if the planet itself was a shell, with vast inner chambers or even entire worlds inside? In the 17th century, the astronomer Edmund Halley, better known for the comet that bears his name, gave the hollow Earth theory its most serious scientific form. Observing irregularities in Earth's magnetic field, Halley suggested in 1692 that our planet might consist of a hollow shell about 500 miles thick, containing two inner concentric shells and a solid core. Between these shells, he speculated, lay luminous atmospheres. Perhaps the aurora borealis, he proposed, was caused by gases escaping from vents in the polar regions. Halley's model was bold, but it carried authority. Here was no wild mystic but a respected scientist of the Royal Society. His version of the hollow Earth entered the conversation of serious natural philosophy, debated and modified by others. Some imagined great central fires warming the interior, others entire subterranean oceans. A few even proposed that life might exist there, strange creatures inhabiting inner lands, shielded from the surface. By the 18th and 19th centuries, the theory leapt into popular imagination. Writers spun tales of hidden kingdoms inside the Earth. Jules Verne's Journey to the Center of the Earth carried readers through caverns of prehistoric beasts and vast underground seas, blending science with fantasy. Simms Hole, proposed by American Army officer John Cleves Simms Jr., suggested vast openings at the poles leading into the hollow world. Simms campaigned passionately, publishing pamphlets and lobbying Congress to fund expeditions. He died without success, but his followers continued to spread the vision of an inner Earth. The hollow Earth also attracted mystics and occultists. Some claimed that lost civilizations such as Atlantis had migrated inward rather than vanished. Others spoke of spiritual beings dwelling inside, guiding humanity in secret. Theosophical writings in the 19th century described subterranean masters, blending science fiction speculation with esoteric tradition. For believers, the inner Earth was not just geology but prophecy. Why did the theory endure so long? In part because the Earth's interior was inaccessible. Unlike the stars or oceans, it could not be directly studied. Without evidence, imagination had free rein. The hollow model also answered questions of magnetism, earthquakes, and volcanoes, phenomena that lacked clear explanation at the time. It offered coherence, even if that coherence rested on shaky ground. Eventually, evidence mounted against it. Seismology in the 20th century revealed how earthquake waves passed through Earth, mapping its interior layers with precision. The results showed not vast empty chambers, but solid mantle, liquid outer core, and dense inner core. Gravity, density, and physics all confirmed that Earth was filled, not hollow. The hollow Earth theory collapsed as science advanced, joining the catalog of charming but discredited ideas. And yet, like many forgotten theories, it never fully died. It lingers in folklore, conspiracy theories, and fiction. Hollow Earth myths appear in adventure novels, films, and even fringe claims about UFOs and secret polar openings. Though science has closed the door, imagination has kept it ajar. The hollow Earth speaks to a human impulse to populate the unknown with wonder. Where we cannot see, we invent. Caves and tunnels have always carried mystery, leading inward to places of secrecy and transformation. To imagine an entire world beneath our feet is to give shape to the hidden, to dream of other realms just out of reach. Picture an explorer standing on Arctic ice in the 19th century, peering toward the horizon, convinced that somewhere lies an opening into another world. Or a philosopher in Halley's time, sketching concentric shells within the globe, imagining luminous skies beneath our own. They were wrong about the geology, but not wrong to wonder. Their error was a stage in the larger story, the quest to know what lies beneath, and the recognition that even the ground we stand on once felt like an undiscovered world. Martian canals. Life on Mars. At the end of the 19th century, the human imagination lifted its eyes to the night sky and found a neighbor that seemed almost familiar. Mars, with its reddish hue and shifting seasons, looked tantalizingly Earth-like through the telescopes of the time. Astronomers sketched dark patches they called seas, pale regions they thought were continents, and most mysteriously, long straight lines that crisscrossed the surface. These were the so-called Martian canals, features that for a few decades convinced much of the public and even some scientists that Mars was inhabited by intelligent beings. The story began in 1877 when Italian astronomer Giovanni Schiaparelli used a new telescope to map the planet. He recorded linear markings and called them canali, the Italian word for channels or grooves. When translated into English, however, canali became canals, a term loaded with human implication. A channel might be natural, but a canal was unmistakably artificial. Readers imagined Martian engineers digging massive waterways across their world. The idea caught fire. In an age of great engineering feats like the Suez Canal, it seemed plausible that another civilization might carve similar structures on a planetary scale. Popular science magazines, newspapers, and books spread the story. The canals appeared as proof that Mars was not only alive but intelligent. The most famous advocate was Percival Lowell, a wealthy American who built an observatory in Arizona specifically to study Mars. Lowell published detailed maps of the canals, drawing them in neat geometric grids. He proposed that Mars was a dying world, its inhabitants constructing enormous irrigation systems to carry water from the polar ice caps across the dry planet. In his writings, Lowell described an advanced but desperate civilization, clinging to survival through brilliant engineering. His vision captured the public imagination like few astronomical theories ever had. For years, the Martian canals were taken seriously. Textbooks mentioned them. Lectures described Martian society. Novelists expanded the idea into fiction, most famously H.G. Wells in The War of the Worlds, which transformed Lowell's dying Martians into invaders seeking Earth's resources. The canal theory bridged science and culture, feeding both fascination and fear. Yet from the start, doubts lingered. Not all astronomers could see the canals. Some reported fuzzy, irregular features rather than straight lines. Others argued that Lowell's maps were too precise, suspiciously neat compared to the wobbly, shifting views through telescopes. The more powerful the instrument, the less clear the canals seemed to be. By the early 20th century, many scientists suspected they were illusions, patterns the human eye created out of scattered dots and streaks, much like seeing faces in clouds. As photography advanced, the mystery began to fade. Early images of Mars failed to show the canals clearly. By the 1920s, most professional astronomers had abandoned the theory, though it lived on in popular culture. The decisive blow came with spacecraft. In 1965, NASA's Mariner 4 sent back the first close-up images of Mars. Instead of canals and civilizations, it revealed a cratered, barren landscape. Later missions confirmed the planet's dry, desolate nature. There were valleys, canyons, and evidence of ancient water flows, but no vast geometric waterways, no signs of engineers from another world. The Martian canals were in the end a case study in wishful seeing. Schiaparelli's canali were likely real features blurred by optics, but Lowell's grand grids were artifacts of perception, straight lines invented by the brain to connect faint markings. The canals never existed except in the human imagination, yet their legacy is remarkable. The canal craze inspired public interest in astronomy, fueled science fiction, and even spurred serious discussion about extraterrestrial life. For a time, it made Mars feel less like a distant rock and more like a neighbor with a story of its own. Though false, the theory pushed both scientists and storytellers to ask bigger questions about life in the universe. Why did it grip the imagination so powerfully? Because it told a story we recognized: survival against decline, intelligence building structures to defy fate. In Lowell's vision of Martians battling planetary drought, people saw a mirror of their own industrial age, with its canals, railways, and looming ecological challenges. The Martians were projections of ourselves, distant but familiar. Today, when rovers crawl across Mars, sending back high-definition images, the canals feel quaint, a reminder of how much we once mistook. But they also remind us of something more enduring: how easily we weave hope and fear into the stars. The night sky is not just a place of data, but a canvas for imagination. The Martian canals never existed, but the longing they represented, the hope of not being alone, the dream of intelligence elsewhere, remains as vivid as ever. Piltdown Man, the fake missing link. On a chilly December day in 1912, a group of scientists gathered at the Geological Society of London for an announcement that seemed destined to rewrite human history. Charles Dawson, an amateur antiquarian, unveiled fragments of a skull and jaw he claimed to have unearthed from gravel pits near Piltdown, a village in Sussex. The pieces, he argued, belonged to a previously unknown human ancestor. The skull was large, resembling modern humans, while the jaw was primitive, like that of an ape. Together they seemed to form the long-sought missing link between ape and man. The discovery electrified the scientific world. For decades, evolutionary theory had been gaining ground since Darwin, but fossil evidence for human evolution was still sparse. Piltdown Man, dubbed Eoanthropus dawsoni, Dawson's Dawn Man, appeared to fill the gap perfectly. Newspapers celebrated it as proof of Britain's place at the forefront of science, even joking that humanity's earliest ancestor was, fittingly, an Englishman. The fossil also fit neatly with contemporary expectations. Many European scientists believed that large brains had evolved early, before other human features. The Piltdown skull, with its broad cranium, seemed to confirm this bias. And in an age of intense national pride, Britain welcomed the chance to host such a crucial find on its soil. Piltdown Man was hailed as authentic, studied in universities, and featured in textbooks. For 40 years, it shaped the story of human evolution. But not everyone was convinced. From the start, some researchers noticed oddities. The jaw and skull fragments did not quite match. The teeth showed unusual wear, as though filed down. And other fossil discoveries elsewhere, like the Tong child in South Africa and early Homo erectus specimens in Asia, suggested a different evolutionary path, one in which smaller brains came first. Yet Piltdown's prestige and its defenders' authority kept doubts at bay. Skepticism lingered, but the fossil remained enshrined. The truth unraveled only in 1953, when advanced testing methods were applied. Florian analysis revealed that the skull and jaw were of very different ages. The skull was medieval, only a few hundred years old. The jaw belonged to an orangutan, its teeth deliberately filed to resemble human wear. Microscopic studies showed telltale scratches from the filing and staining to make the bones look ancient. Piltdown Man was exposed as an elaborate hoax, the greatest fraud in the history of paleoanthropology. The revelation stunned the scientific world. How had such an obvious forgery fooled experts for so long? The answer lay partly in confirmation bias. Scientists wanted a fossil that fit their theories of brain-first evolution. Piltdown delivered exactly that. National pride played a role too. Britain, lacking spectacular finds like Germany's Neanderthals or Java's early humans, now had its own ancestral treasure. These expectations blinded many to inconsistencies. As for the perpetrator, suspicion has long centered on Charles Dawson himself, who had a history of questionable discoveries. Others have suggested accomplices, ranging from disgruntled museum staff to rival scientists. To this day, the true culprit is debated, though most historians agree Dawson was at the heart of it. Whoever forged Piltdown carefully combined an ape's jaw with a human skull, filed the teeth, and stained the bones to mimic age. The hoax was designed with cunning precision to exploit the hopes of the scientific community. The Piltdown episode serves as a sobering reminder of science's vulnerabilities. Even brilliant minds can be swayed by desire, prestige, and cultural bias. For decades, Piltdown Man distorted research, steering attention away from genuine fossils that told a different story. It is a case study in how science, though self-correcting, can be led astray for long stretches when skepticism yields to wishful thinking. Yet the story is not one of failure alone. The eventual exposure of the hoax also demonstrates the strength of scientific inquiry. As new fossils emerged and new methods developed, inconsistencies became impossible to ignore. Doubt grew until the evidence overturned illusion. Science stumbled, but it recovered, discarding error and refining its picture of human origins. Today, Piltdown Man is remembered not as a breakthrough, but as a cautionary tale. Museum exhibits present it alongside the truth, showing how easily bias can cloud judgment. It reminds us that discovery must be met with skepticism as well as wonder, that extraordinary claims require extraordinary scrutiny. Imagine again the gravel pits of Sussex, the fragments presented to a room of eager scientists. The skull and jaw, carefully arranged, seemed to whisper of a dawn ancestor, a missing link that confirmed what everyone hoped to find. For decades, that whisper drowned out doubts. But time and evidence spoke louder. The missing link was never there. Only a forgery reflecting human vanity, ambition, and the peril of seeing what we most wish to see. Steady-state universe theory. For centuries, people looked to the night sky and assumed it was eternal. The stars seemed unchanging, the constellations fixed, the heavens permanent. Even as telescopes revealed galaxies far beyond the Milky Way, many scientists held on to this ancient intuition: the universe had no beginning and no end. In the 20th century, this intuition was recast into a scientific framework known as the steady-state theory, a vision of a cosmos eternal, infinite, and forever the same on the largest scales. The theory took shape in 1948 in the hands of three physicists, Fred Hoyle, Hermann Bondi, and Thomas Gold. They were responding to new discoveries that hinted at an expanding universe. If galaxies were rushing apart, as Edwin Hubble's observations suggested, then what did that mean for the past? Extrapolated backward, expansion seemed to imply that everything once was concentrated in a single point, a cosmic birth. Hoyle found this idea distasteful, even giving it a dismissive nickname during a radio broadcast, the Big Bang. The name stuck, but Hoyle did not mean it as praise. Instead, he and his colleagues proposed a radical alternative. The universe was indeed expanding, but as it did, new matter was continuously created. Atoms of hydrogen appeared spontaneously in the vast spaces between galaxies, so slowly and sparsely that the process was invisible to human instruments. These new atoms condensed into stars and galaxies, filling the gaps left by expansion. In this way, the universe remained constant in density and appearance over time. Galaxies might move, but the overall picture of the cosmos, the grand tapestry of stars, was unchanging. The elegance of steady state lay in its philosophical appeal. It preserved the idea of an eternal universe, with no creation moment and no end. It avoided the unsettling notion of a singularity, a beginning beyond physics. It also echoed an older principle, the cosmological principle, the idea that the universe is uniform and isotropic, looking the same in all directions and at all times. In steady state, the cosmos was not only homogeneous in space, but also in time, always the same, everywhere, forever. For a while, the theory had traction. It explained Hubble's expansion without invoking a beginning. It also predicted something testable. The average properties of the universe, such as density and appearance, would remain unchanged as time passed. Galaxies far away, and therefore seen in the distant past, should look much like those nearby. If true, the telescope would reveal a timeless cosmos. But as astronomy advanced, cracks appeared. In the 1950s and 1960s, radio astronomy detected galaxies and quasars far more numerous in the distant universe than in the nearby one. This suggested that the cosmos was evolving, not steady. Then in 1965 came the decisive discovery, cosmic microwave background radiation, the faint afterglow of a hot, dense early universe, predicted by the Big Bang model, but not by steady state. The radiation was quickly accepted as overwhelming evidence against Hoyle's vision. Despite this, Hoyle and others defended the theory, proposing modifications and alternatives. Some suggested that matter creation events occurred in bursts, or that the microwave background could be explained by light scattered from distant dust. But the weight of evidence continued to favor the Big Bang. The abundance of light elements, the large-scale structure of galaxies, and the detailed properties of the cosmic background all lined up with a universe that had a fiery beginning about 13.8 billion years ago. By the 1970s, steady state had largely faded from mainstream science. It survives now only in historical discussions and in a few speculative modifications, like Hoyle's later quasi-steady state model. Its failure, however, does not diminish its significance. For 2 decades, it provided a genuine competitor to the Big Bang, forcing both sides to refine their predictions and seek clearer evidence. In this way, even a wrong theory advanced science by sharpening the questions. Why does steady state remain fascinating, even as a forgotten theory? Because it reflects a human longing for permanence. To imagine an eternal universe is to imagine ourselves within an endless backdrop without beginning or end. The Big Bang, by contrast, forces us to grapple with creation and with cosmic history, with a universe that changes and evolves. Hoyle's resistance was not only scientific but philosophical. He disliked the intrusion of theology into cosmology, fearing that a universe with a beginning would invite religious interpretations. In some sense, the steady-state theory was both a scientific proposal and a cultural defense of eternity. Imagine gazing through a telescope in the 1950s, sketching distant galaxies, convinced you are seeing what has always been and what always will be. The steady, unchanging cosmos offers comfort, a stage set forever. Then imagine, a decade later, listening to the static on a radio antenna, realizing it is not noise but a whisper from the birth of time itself. The steady stage vanishes, replaced by a drama with a beginning, middle, and eventual end. The steady-state theory is gone as science, but it lives as a reminder. Even false universes can guide us toward truth. Its elegance shows how deeply we value permanence, and its downfall shows how evidence can overturn even the most appealing visions. In the ashes of its collapse, the Big Bang rose stronger, carrying with it not only equations but a story that the universe has a history, that we inhabit its unfolding chapters, and that change, not eternity, is the deepest law of all. Cold fusion claims of 1989. In March of 1989, two chemists, Martin Fleischmann and Stanley Pons, stood before cameras at the University of Utah and announced something that sounded like a miracle. They claimed to have achieved nuclear fusion at room temperature in a tabletop experiment. No massive reactors, no million-degree plasmas, no sprawling laboratories, just a jar of heavy water, a palladium electrode, and the promise of almost limitless clean energy. If true, the discovery would have changed the world overnight. Fossil fuels would become obsolete, power shortages would vanish, and humanity would enter a new technological age. The announcement made headlines worldwide, and cold fusion was on every tongue. Fusion itself was already well known. In the heart of stars, hydrogen nuclei smashed together to form helium, releasing enormous amounts of energy. Scientists had long tried to reproduce this in reactors on Earth, but the conditions required, temperatures hotter than the sun, immense magnetic fields, made it fiendishly difficult. Fleischmann and Pons claimed to have bypassed these hurdles with a deceptively simple setup. By loading palladium electrodes with deuterium from heavy water, they said, the atoms were pressed so close together that fusion occurred spontaneously. The cell gave off excess heat, too much to be explained by chemistry alone. This, they argued, was proof of nuclear reactions happening at room temperature. The announcement was electrifying, but also unconventional. Instead of publishing quietly in a peer-reviewed journal, the chemists went directly to the press. The media painted pictures of a future of cheap, abundant, and safe energy. Governments and companies rushed to investigate. Laboratories across the world scrambled to replicate the results. For a few months, it seemed as though humanity was on the brink of solving its greatest energy challenge. But replication proved elusive. Some groups reported puzzling excess heat, others found nothing unusual. A few claimed traces of nuclear byproducts like neutrons or tritium, but the levels were inconsistent and far too low to account for the claimed heat. Within weeks, skepticism mounted. Physicists pointed out that if fusion were truly occurring at the claimed scale, dangerous radiation should have been detected. It wasn't. By the end of 1989, a consensus was forming. The evidence was weak, the claims overstated. Panels convened by the U.S. Department of Energy concluded that the results did not support nuclear fusion. Funding dried up, reputations faltered, and cold fusion became a cautionary tale. Fleischmann and Pons, once hailed as visionaries, were criticized for bypassing scientific protocols, for announcing too soon, for chasing fame. And yet the story is not so simple. Some researchers continued to study the phenomenon, rebranding it as low-energy nuclear reactions. They argued that while Fleischmann and Pons may have overreached, there were anomalies worth exploring, small but unexplained bursts of heat or rare nuclear signatures. Even today, a small community of scientists and engineers continues to test such claims, though mainstream physics remains unconvinced. Why did cold fusion capture such attention, even briefly? Because it embodied both fear and hope. In the late 1980s, the world worried about nuclear energy's dangers, the looming climate crisis, and the limits of fossil fuels. Cold fusion promised an elegant solution, endless power free of pollution and radiation. It was a story too good to ignore. When the evidence collapsed, disappointment was fierce, but the dream lingered. Cold fusion's brief rise and fall illustrates the delicate balance of science. On one hand, bold claims push boundaries and inspire new possibilities. On the other, without careful replication and peer review, they risk leading millions astray. The episode became a lesson in scientific humility, that extraordinary claims demand extraordinary evidence, and that publicity cannot substitute for proof. And yet, in a way, the cold fusion affair still carries value. It pushed researchers to refine their tools, sharpen their skepticism, and revisit assumptions about matter at small scales. Even failures contribute to progress, leaving behind data, cautionary tales, and sometimes seeds for future discovery. Imagine the scene in 1989: television cameras, flashing bulbs, two chemists at a podium promising a revolution. In that moment, people glimpsed a world transformed, where a glass of water might power a city. For a heartbeat in history, hope burned as brightly as any fusion reaction. Then the light dimmed, leaving behind a story of ambition, error, and the enduring human hunger for miracles. Crystalline spheres of the heavens. Look up at the night sky without the filter of modern science. The stars are not distant suns, not galaxies swirling billions of light years away. They are points of light fixed in place, glittering on a dark dome that seems to arch above Earth. To ancient eyes, this dome was not a metaphor. It was literal, a solid structure holding the stars, turning overhead each night. As astronomy matured, the dome evolved into a sophisticated model, a system of crystalline spheres, each carrying planets and stars in perfect eternal motion. The concept was shaped most famously by Claudius Ptolemy in the 2nd century CE, though it drew on earlier Greek thought, especially that of Aristotle. The idea was that Earth stood immovable at the center of the cosmos. Around it were nested transparent spheres, like the layers of an onion, each turning with clockwork precision. The moon rode on the innermost sphere, then Mercury, Venus, the Sun, Mars, Jupiter, and Saturn, followed by the sphere of fixed stars. Beyond all these lay the primum mobile, the first moved which turned all the others. Each sphere was imagined as solid, crystalline, yet invisible, real enough to carry the heavenly bodies, but too subtle for human senses to detect. The appeal of this model was enormous. It gave structure to the sky. The unpredictable wandering of planets was explained as the motion of their spheres. Retrograde movement, eclipses, and seasonal changes were all folded into this cosmic machinery. The heavens, once a chaos of lights, became an ordered system, and because circles and spheres were considered the most perfect forms, the crystalline heavens embodied divine harmony. For centuries, this vision shaped both science and theology. The Church found it useful. The ordered spheres spoke of a cosmos created with purpose. The outermost sphere, where God or the angels might dwell, set all others in motion, connecting physics with metaphysics. Medieval scholars wove the spheres into grand cosmologies that linked astronomy, music, and philosophy. The music of the spheres was thought to be the harmony created by their motions, a cosmic symphony inaudible to human ears but resonant in the soul. Artists and poets gave the spheres vivid life. Dante's Divine Comedy carries the pilgrim through the nested heavens, from the moon's pale sphere upward through the planets, to the fixed stars, and finally to the Empyrean, the realm beyond all spheres where God resides. To medieval readers, Dante was not inventing but describing the structure of reality itself. The crystalline spheres were as real as mountains or seas. And yet, for all its elegance, the model carried difficulties. Astronomers added epicycles, small circles upon circles, to account for planetary motions that spheres alone could not explain. The machinery grew ever more elaborate, a celestial clock patched with gears. Still, the crystalline spheres endured because they matched both observation and philosophy. The heavens moved as if mounted on wheels, so wheels they must be. The turning point came with the Renaissance. Nicholas Copernicus placed the sun at the center, simplifying the dance of planets. Johannes Kepler discovered that orbits were not circles but ellipses, dissolving the need for rigid spheres. Galileo's telescope revealed mountains on the moon, moons orbiting Jupiter, and imperfections in the heavens that shattered the notion of crystalline perfection. The spheres cracked, and with them cracked the old harmony of the cosmos. By the 17th century, the spheres had vanished from serious astronomy. Space was no longer a set of nested shells, but a vast, open expanse where bodies moved freely, under laws of motion and gravity. The crystalline architecture dissolved into abstraction. What once seemed solid and eternal was forgotten, a relic of imagination. Yet the spheres left a profound legacy. They were not only a theory of astronomy, but a way of imagining order. They gave generations a sense of place in a structured universe. Even as science advanced, echoes of the spheres remain, in our language, in metaphors of harmony, in the way we still picture orbits as neat tracks. And in a deeper sense, the dream of order they represented lives on in physics today, as scientists search for unifying principles to make sense of the cosmos. Imagine the medieval scholar gazing upward, convinced that above him vast transparent shells revolved with solemn grace, carrying the planets on their eternal paths. He cannot know of gravity or galaxies, but he knows the comfort of order, the music of a cosmos that makes sense. His crystalline heavens are gone now, replaced by relativity and quantum fields, but his desire for harmony is still ours. Forgotten as science, the spheres remain as a reminder when we look at the sky, we are always building structures to hold our wonder, even if they later dissolve. Absolute space and time. Pre-relativity. Stand in a quiet field and close your eyes. You feel the ground beneath you, the air brushing your face, the slow pull of gravity holding you steady. If you imagine moving, you picture yourself in a vast stage, a backdrop of space that exists whether you are in it or not. And as moments tick by, you feel time flowing, carrying you forward like a river that never stops. For centuries, this intuition hardened into doctrine. The universe was built upon absolute space and absolute time, eternal frameworks that existed independently of anything within them. The most influential architect of this vision was Isaac Newton. In his Principia Mathematica of 1687, he distinguished between relative and absolute motion. To Newton, a carriage rolling down a road was in relative motion compared to the ground, but whether the entire earth itself spun or drifted through the heavens required another kind of measure. For him, such questions could only be answered by positing an invisible stage, absolute space. It did not bend or move. It was the fixed arena in which all motion occurred. Likewise, absolute time flowed uniformly, the same for every observer regardless of their speed or location. Newton's reasoning was partly philosophical, partly practical. The laws of motion and gravitation needed a universal reference frame. How else to define inertia? Motion continuing in a straight line, if not against the backdrop of something unmoving. He even offered a famous thought experiment, a bucket of water spun by its handle. As it rotated, the water's surface curved upward at the edges, forming a concave shape. The curvature, Newton argued, proved that the water was rotating not merely relative to the bucket, but relative to absolute space itself. For 2 centuries, Newton's absolutes dominated science. They gave physics a sturdy foundation. The planets circled the sun along predictable paths, measured in absolute time and positioned in absolute space. Engineers built machines, navigators charted seas, astronomers mapped the heavens, all with confidence that the universe's backdrop was fixed and unchanging. But beneath this confidence, cracks began to show. In the 19th century, the nature of light raised troubling questions. If light was a wave, as experiments suggested, what was its medium? Sound required air. Ripples required water. Physicists proposed the luminiferous Aether as the invisible substance filling absolute space, carrying light waves across the cosmos. Yet when Albert Michelson and Edward Morley tried to detect Earth's motion through this Aether in 1887, they found nothing. Light's speed appeared constant, unmoved by Earth's journey through space. The absolute backdrop wavered. At the same time, philosophers like Gottfried Wilhelm Leibniz had long challenged Newton's absolutes, arguing that space and time had no reality apart from the relations between objects and events. Space was not a container but a web of distances. Time was not a flowing substance but an order of succession. These relational views remained in the background for centuries until physics itself caught up. The revolution came in 1905, when Albert Einstein published his special theory of relativity. He abolished the need for absolute space and time. Instead, motion could only be described relative to other motion, and time could tick differently for different observers depending on their speed. A decade later, in general relativity, Einstein went further. Space and time were not rigid containers, but a flexible fabric, space-time curved by matter and energy. Gravity was not a pull across absolute space, but the bending of this cosmic geometry. The absolutes of Newton dissolved into relativity. Looking back, absolute space and time appear as one of science's most influential errors. They were not real in the way Newton imagined, but they provided a framework stable enough to guide discovery for centuries. Without the absolutes, perhaps mechanics would not have advanced so quickly, navigation and astronomy would not have thrived, and the stage would not have been set for Einstein's revolution. Like scaffolding removed after construction, Newton's absolutes were discarded only once something stronger stood in their place. And yet, the intuition remains. We still speak of time flowing, of space as a container. Our daily experience feels Newtonian, even though the cosmos is relativistic. The forgotten absolutes still haunt our language, our imagination, and even our metaphors for existence. Picture Newton himself, staring into the night sky, convinced that the stars hung in a vast and unmoving theater, each celestial body moving against an eternal backdrop. He was wrong about the stage, but right to build a vision of order. The stage has shifted. It bends, it stretches, it flows differently depending on the observer. But the desire that drove Newton, the need to find a framework for reality, still drives us. Absolute space and time are gone, yet they remind us that every framework is temporary, each destined to be replaced by something stranger and perhaps truer. Catastrophism in geology. Walk across a rocky cliffside and look closely at the layers exposed there. Some are thin bands of sandstone, others thick slabs of limestone or shale. To modern eyes, each layer tells a slow story of rivers, seas, and shifting continents over millions of years. But for centuries, such patience was unthinkable. Mountains, valleys, and seas, people believed, were shaped not by slow processes, but by sudden, violent events, catastrophes that struck with overwhelming force. This was the doctrine of catastrophism. The idea had ancient roots. Myths across cultures described floods, fires, and upheavals that reshaped the world. The story of Noah's flood in the Bible, or similar tales from Mesopotamia, India, and the Americas, offered a powerful narrative disaster as the sculptor of landscapes. When early naturalists examined fossils of marine creatures high in mountains, it seemed obvious to them that such anomalies were the remnants of great floods. If shells lay far from the sea, what else but catastrophe could have lifted them there? In the 17th and 18th centuries, catastrophism became the dominant framework in geology. Thinkers like Thomas Burnet and John Woodward argued that Earth's features were carved by singular cataclysmic events, often tied to biblical floods. The strata of rock were interpreted as sediment dumped in layers during these immense disasters. Mountains were upheavals from sudden convulsions of the crust. Valleys were gouged out in moments of unimaginable violence. The most influential catastrophist was the French naturalist Georges Cuvier in the early 19th century. A master of comparative anatomy, Cuvier studied fossils and noticed patterns of extinction. He concluded that Earth's history was punctuated by a series of catastrophes, vast floods or upheavals that wiped out species. After each, new creatures appeared, repopulating the world. Cuvier rejected evolutionary change over long timescales, arguing instead that destruction and renewal were the engines of history. For him, the bones of mammoths and giant sloths were not ancestors of today's animals, but casualties of past cataclysms. Catastrophism held great appeal. It explained the evidence quickly, without the need for unimaginable spans of time. It fit comfortably with religious traditions of sudden creation and flood. And it matched human experience. Disasters were visible, dramatic, and powerful, while slow erosion was subtle, almost invisible. A single earthquake could transform a landscape overnight. Why not imagine Earth itself shaped the same way? But not all were convinced. In Scotland, James Hutton proposed a different view. Observing rivers carving valleys and sediments building new layers, he argued that small, gradual processes, given enough time, could shape the Earth. No vestige of a beginning, no prospect of an end, he wrote in 1788, suggesting a vision of deep time. Later, Charles Lyell expanded this view in his Principles of Geology, promoting uniformitarianism, the idea that the present is the key to the past. Earth's features were not products of singular catastrophes, but of patient forces, erosion, deposition, volcanism, repeated endlessly over millions of years. The debate between catastrophists and uniformitarians defined early geology. Catastrophism offered drama, aligning with biblical narrative. Uniformitarianism offered continuity, aligning with emerging scientific evidence. Over time, the steady accumulation of geological data, fossil sequences, radiometric dating, and plate tectonics sided with uniformitarianism. Earth's history was not a handful of violent chapters, but a vast, slow novel written in stone. Yet catastrophism did not vanish completely. In the 20th century, hints of its return appeared in new guises. The discovery of meteor craters and the theory that a giant asteroid impact ended the age of the dinosaurs in what is called the Cretaceous-Paleogene extinction event revived the idea that sudden cataclysms play a role in Earth's story. Volcanic supereruptions, ice ages, and mass extinctions all revealed that catastrophe and gradualism are not enemies but partners in shaping the planet. Today, catastrophism is forgotten as the all-encompassing explanation it once was, but not as a piece of the puzzle. It reminds us that landscapes bear both the marks of patient rivers and sudden shocks. The Grand Canyon speaks of slow erosion, but a single volcanic eruption can erase forests in hours. Earth is not ruled by one tempo, but by many. Why did catastrophism endure for so long? Because it matched human imagination. Sudden disasters are visible, memorable, and terrifying. A flood or an earthquake leaves scars in a day. Erosion takes centuries to notice. Our minds prefer the dramatic to the subtle. Catastrophism was, in a sense, geology shaped by storytelling instinct. Picture a naturalist in Cuvier's Paris, laying out fossil bones of strange beasts no longer alive. He imagines the world torn apart by floods, continents drowned and reborn, creatures swept away in hours. His vision is wrong in scale, but not entirely in spirit. Catastrophe does leave its mark. It just shares the stage with time's slower hand. Catastrophism is forgotten as a ruling theory, but it whispers a truth that change is not always gentle. Earth's story is written in both whispers and shouts, in the slow layering of sediment and the sudden roar of disaster. And in remembering this, we remember that the ground beneath us, though it feels steady, is never truly still. N-ray phenomenon and physics. In the early 1900s, physics was brimming with discovery. Wilhelm Röntgen had revealed X-rays in 1895. Henri Becquerel had uncovered radioactivity, and Marie and Pierre Curie were unraveling the secrets of radium. The world seemed alive with invisible forces, each new revelation more astonishing than the last. It was in this fevered atmosphere that a French physicist, Prosper René Blondlot, announced the discovery of yet another invisible marvel, a new kind of radiation he called N-rays. In 1903, Blondlot, a respected professor at the University of Nancy, described experiments in which metals emitted faint rays under certain conditions. These rays, he claimed, could pass through substances and slightly increase the brightness of a spark or an illuminated surface. Unlike X-rays, they could not be captured on photographic plates, but Blondlot insisted they were real, detectable through careful observation of light's faint intensification. He named them N-rays after his home city of Nancy. The announcement came at a time when the scientific community was primed to believe in hidden energies. Laboratories across Europe rushed to test Blondlot's claims. Within a year, more than 100 papers were published on N-rays. Researchers reported detecting them from nearly every substance, metals, living tissues, even the human nervous system. Some claimed N-rays could improve eyesight, sharpen the edges of shadows, or reveal details invisible to the naked eye. To many it seemed the dawn of another revolution in physics. Yet the evidence was fragile. N-rays could not be photographed, measured, or isolated with instruments. Their presence was inferred only by subtle changes in light seen by human observers. Detection required darkened rooms, patience, and a trained eye. The results were subjective, and critics began to whisper that expectation, not radiation, was shaping what scientists thought they saw. The turning point came in 1904, when the American physicist Robert W. Wood, known for his skeptical investigations, visited Blondlot's laboratory. During a demonstration, Wood quietly removed a crucial prism from the apparatus without telling Blondlot. Blondlot and his assistants continued to report seeing N-rays exactly as before, oblivious to the missing component. To Wood, this confirmed that the phenomenon was not physical but psychological. His published account cast serious doubt on N-rays, and the scientific tide quickly turned. By 1905, enthusiasm had collapsed. What had seemed a flood of discovery dried up into embarrassment. N-rays were recognized as an illusion, born of suggestion, fatigue, and the eagerness to join in a fashionable discovery. Blondlot, once respected, saw his reputation ruined. He continued to insist on the ray's reality, publishing occasional defenses, but his colleagues had moved on. The episode became a cautionary tale in scientific history. Why did so many believe for so long? Partly because the moment was ripe. The discovery of X-rays and radioactivity had transformed physics, showing that the world was full of unseen forces. Scientists were eager for more. When Blondlot claimed to have found another invisible phenomenon, the community was ready to accept it. Confirmation bias, seeing what one expects to see, did the rest. The N-ray affair is often remembered as a case of self-deception in science. Observers were not lying. They truly believed they saw faint brightening, subtle shifts in light. But expectation shaped perception. When many people anticipate an effect, their senses can deliver it even in its absence. The N-ray story became a classic example of the importance of objectivity, instrumentation, and blind testing, lessons that helped sharpen experimental rigor in the 20th century. And yet the story is not only one of folly. Even false discoveries can play a role in science's progress. The N-ray debacle forced researchers to confront the unreliability of human observation, especially when effects are faint. It encouraged the adoption of photographic plates, sensors, and quantitative methods over the subjective reports of the eye. In this way, the ghost of N-rays contributed indirectly to the discipline's growth. Imagine Blondlot in his darkened lab, straining his eyes at the flicker of a spark, convinced he perceives a new form of radiation. His excitement is genuine, his conviction unshaken. Around him, assistants nod, eager to please and to share in the thrill of discovery. They are wrong, but their error is deeply human. The desire to find, to belong to a moment of revelation, can be stronger than caution. Today, N-rays are forgotten except as a cautionary tale in textbooks, but their story endures as a reminder. Science is not immune to illusions, and even brilliant minds can see what is not there. Out of such mistakes, however, comes progress. In learning to guard against self-deception, science grows stronger. The invisible forces that shape the universe are real, but not every shadow in the laboratory belongs to them. Animal magnetism, Mesmer's force. In a dim salon in late 18th century Paris, fashionable men and women gathered in a darkened room. Curtains were drawn, the air heavy with incense. In the center stood a large wooden tub filled with water and iron filings, its lid pierced with rods that patients grasped. Around it sat dozens of people, waiting in silence. The physician Franz Anton Mesmer moved among them, dressed in silk, carrying a magnetic wand. With slow gestures he directed an invisible force through their bodies. Some trembled, some wept, others swooned into trances. They believed they were being healed by animal magnetism, the mysterious fluid Mesmer claimed governed health and disease. Mesmer was an Austrian physician, trained in medicine, but drawn to the frontiers of science. In the 1770s, he proposed that the universe was filled with a subtle fluid similar to the magnetism studied in physics, but uniquely connected to living beings. This fluid, he said, flowed through the body, ensuring harmony between organs, mind, and cosmos. Illness arose when its flow was blocked or unbalanced. By manipulating it, using magnets at first and later the gestures of his own hands, Mesmer believed he could restore equilibrium. The idea was not entirely out of step with its time. Electricity and magnetism were new and fashionable sciences. Invisible forces had suddenly become real, measurable, and transformative. Mesmer simply extended the concept into the human realm. He called his version animal magnetism to distinguish it from ordinary mineral magnetism. Where physicists saw forces in lodestones and wires, Mesmer saw them in nerves and blood. In Paris, Mesmer became a sensation. Patients claimed relief from pain, paralysis, and melancholy. The group sessions he led were theatrical, dim rooms, music played on a glass harmonica, dramatic passes of his hands. People often fell into crises, convulsions, or trance-like states that Mesmer interpreted as evidence of blocked fluid being released. Word spread quickly, and the wealthy elite flocked to his salons. To some he was a visionary healer, to others a dangerous charlatan. The French authorities eventually intervened. In 1784, King Louis XVI appointed a commission of leading scientists, including Benjamin Franklin and Antoine Lavoisier, to investigate Mesmer's claims. Their conclusion was damning. They found no evidence for any magnetic fluid. The effects, they argued, arose from imagination, suggestion, and the power of expectation. The cures were psychological, not physical. With this verdict, official medicine dismissed animal magnetism. And yet the story does not end there. Even stripped of its fluid, Mesmer's methods revealed something real: the strange influence of mind on body, the power of belief and suggestion, the trances, the convulsions, the relief of symptoms, all hinted at psychological forces not yet understood. Later practitioners, building on Mesmer, developed what came to be known as hypnosis. The very word mesmerize survives in our language, a trace of his influence. For nearly a century after Mesmer, mesmerists continued to practice across Europe and America. Some claimed to heal, others to entertain with stage demonstrations. Physicians cautiously experimented with hypnosis as an anesthetic before surgery. Though animal magnetism as a fluid was abandoned, the recognition that suggestion could alter perception, sensation, and even pain became one of Mesmer's unintended legacies. Why did Mesmer's theory capture so many? Because it offered an explanation that united body, mind, and cosmos in a single vision. Patients longed for meaning in their illnesses, and Mesmer gave them a story in which their suffering was not random, but the result of a blockage that could be released. His ceremonies provided ritual, community, and attention, things often missing in traditional medicine. Even when the fluid was an illusion, the care was real. Modern science looks back on animal magnetism as a forgotten theory, a mix of showmanship and misplaced physics. Yet it also marks a turning point. By exposing the role of imagination and belief in healing, Mesmer inadvertently opened the door to psychology. His failure helped birth a new science of the mind. Picture that Parisian salon once more: the heavy air, the hushed anticipation, the trembling patience, the physician's slow gestures. To them, an invisible fluid was flowing, restoring health. To us, it was the power of expectation, ritual, and the human need for explanation. Mesmer was wrong about magnetism, but not about the depth of the mind's influence. His forgotten force is a reminder that healing has always been more than mechanics. It has always involved the stories we tell ourselves about what moves within us. Ether drag theories. At the dawn of the 19th century, physicists were convinced of two things. First, that light behaved as a wave, and second, that waves required a medium. Just as sound ripples through air and water ripples through the sea, light waves must ripple through something. This something was the luminiferous ether, the invisible substance thought to fill all of space. But if Earth moved through this ether while orbiting the Sun, then strange effects should appear in experiments. To reconcile theory with observation, scientists developed what came to be called ether drag theories, attempts to explain how the Earth and its atmosphere might carry, distort, or partially drag the ether along with them. The basic problem was simple. If Earth truly plowed through the ether, then the speed of light should vary depending on whether one measured it with or against the planet's motion. Astronomers even expected to see ether winds, detectable shifts in starlight caused by Earth's movement through the medium. Some experiments hinted at such effects, while others failed to show anything at all. The contradictions forced new speculation. Maybe the ether wasn't entirely fixed. Maybe Earth, like a ship dragging water in its wake, tugged at the cosmic medium around it. One of the first to suggest such an idea was Augustin Fresnel in 1818. Famous for his work on wave optics, Fresnel proposed that the ether could be partially dragged by transparent materials. He developed a formula for the amount of drag, predicting that light traveling through moving glass or water would be shifted by a fraction of the medium's velocity. Remarkably, later experiments confirmed his prediction. The famous Fizeau experiment of 1851, in which light was passed through moving water, showed exactly the partial drag Fresnel described. It seemed to prove that ether drag was real. Other scientists extended the idea. Some imagined that Earth fully carried the ether in its immediate vicinity, like an atmosphere preventing any ether wind from being detected on the surface. Others suggested only partial drag, with light influence depending on density and medium. These refinements kept the ether alive, sustaining the belief that the mysterious medium was both necessary and consistent with observation. But the puzzle deepened. When Albert Michelson and Edward Morley performed their now famous experiment in 1887 to detect the Earth's motion through ether, they expected to see a shift in light's interference pattern as Earth sped through space. They saw nothing. The speed of light appeared constant, unaffected by direction or supposed ether winds. Ether drag theories could patch some observations, but not this one. The medium grew more elusive, the harder physicists tried to pin it down. To salvage the idea, new proposals were made. Perhaps objects moving through the ether contracted slightly, masking the effects, a hypothesis put forward by George Fitzgerald and Hendrik Lorentz. Their contraction theory explained Michelson and Morley's null result, but at the cost of adding yet another ad hoc adjustment. The ether became like an ever-receding mirage, modified to fit every contradiction, but never directly revealed. The stalemate lasted until 1905, when Albert Einstein swept the whole structure away with his special theory of relativity. Einstein eliminated the need for an ether entirely. Light's constant speed was not the result of drag or hidden forces, but a fundamental property of space-time itself. The contractions and time dilations others had treated as fixes were, in Einstein's vision, natural consequences of relative motion. Ether drag theories, with all their ingenuity, evaporated in an instant. And yet they had not been wasted. Fresnel's formula for partial drag, though derived from an imaginary medium, remains consistent with modern physics, now explained by the interaction of light with matter. The failed attempts to detect the ether refined instruments, inspired precision experiments, and pushed science toward deeper insights. Even wrong turns can build the road to truth. Why did ether drag theories persist for so long? Because they answered a powerful intuition. Waves require a medium. The human mind resists the idea of oscillations in nothingness. To imagine light moving without support seemed absurd. The ether was a comfort, and drag theories gave it flexibility. Only when relativity redefined the stage itself as spacetime rather than substance could physics finally abandon the old intuition. Picture Fresnel at his desk, sketching calculations that predict how water moving in a pipe would tug at the ether, bending the path of light. He is wrong about the substance, but right about the effect. His work leads to experiments that, decades later, help dismantle the very theory he defended. In this way, ether drag theories are forgotten, not because they were useless, but because they were stepping stones. They carried science forward until the bridge of relativity replaced them. Ptolemaic cosmology's last defenses. For nearly 1,500 years, the name Ptolemy carried the weight of certainty. His Almagest, written in the 2nd century CE, described a universe centered on Earth, surrounded by nested spheres carrying the moon, sun, planets, and stars. The system was intricate, adorned with epicycles and deferents to account for the wandering motions of the heavens. To generations of scholars, it was not just a theory, but the truth itself, a cosmos both mathematically precise and philosophically satisfying. Even after Copernicus placed the sun at the center in the 16th century, Ptolemy's geocentric vision did not vanish overnight. Many resisted the heliocentric model, clinging to the old order with arguments sharpened by tradition, theology, and the limits of observation. The last defenses of Ptolemaic cosmology were mounted not by cranks or obscurantists, but by intelligent thinkers who could not yet see enough evidence to abandon the structure that had guided astronomy for centuries. The resistance had several roots. First, the Copernican system, at least in its original form, was not obviously simpler. To preserve circular motion, Copernicus still used epicycles to the naked eye. Earth did not move, the ground felt stable, and no wind of motion was felt. If Earth truly rushed through space, why did birds not get left behind in flight? Why did stones not fall westward as the planets spun beneath them? These were genuine puzzles in a world without Newton's laws to explain inertia and motion. Second, the Ptolemaic system aligned closely with Aristotelian philosophy, which divided the cosmos into an earthly realm of change and a heavenly realm of perfection. Circles and spheres embodied divine harmony. To abandon Ptolemy was to abandon not just astronomy, but a philosophical structure that underpinned medicine, theology, and metaphysics. Scholars trained for centuries in this framework could not easily discard it. Third, religious tradition lent weight to geocentrism. Biblical passages spoke of the earth being fixed, the sun rising and setting. While interpretations varied, the cultural inertia was strong. The Copernican model seemed not only scientifically radical, but theologically dangerous, displacing humanity from the center of creation. Defenders of Ptolemy in the late Renaissance refined their case with skill. The Danish astronomer Tycho Brahe offered a hybrid compromise. The sun orbited Earth, but the other planets orbited the sun. This geoheliocentric model preserved Earth's centrality while capturing the elegance of Copernican orbits. Tycho's system gained significant traction, especially among those unwilling to surrender Earth's privileged place. For a time, it rivaled both Copernican and Ptolemaic cosmologies. But cracks grew wider. The telescope, invented in the early 17th century, dealt heavy blows to the old cosmos. Galileo observed the phases of Venus, which made sense under Copernicus, but were nearly impossible to reconcile with Ptolemy. He saw moons circling Jupiter, proof that not everything revolved around Earth. Slowly, observational evidence began to undermine the old defenses. Still, even into the 17th century, Ptolemaic cosmology had advocates. Some argued that the telescope itself was untrustworthy, introducing distortions. Others proposed increasingly complex arrangements of epicycles to preserve geocentrism. To them, the dignity of tradition outweighed the allure of novelty. Better to trust the wisdom of centuries than the strange new claims of iconoclasts. The final collapse came with Kepler's laws of planetary motion and Newton's theory of gravitation. Elliptical orbits explained the heavens more cleanly than epicycles ever had. Newton's mechanics showed why Earth could move without dislodging birds or stones, because motion persists unless acted upon. The intellectual scaffolding that had supported Ptolemy crumbled. By the 18th century, geocentrism survived only as a curiosity. Looking back, the last defenses of Ptolemaic cosmology are not merely stubbornness. They remind us that science is not only about data, but about worldviews, habits of thought, and the difficulty of leaving behind a structure that feels coherent. Ptolemy's system endured because it worked well enough, because it was elegant, and because it was woven into the fabric of philosophy and faith. To abandon it required not just new facts, but a new imagination. And yet there is something poignant about those last defenders, sketching epicycles, adjusting spheres, resisting the tide of change. They were wrong, but not foolish. They were grappling with a transition as profound as any in human thought, from an Earth-centered cosmos to a sun-centered universe, and eventually to a galaxy among countless galaxies. Their resistance is a reminder that knowledge advances not only by discovery, but by persuasion, debate, and the slow surrender of cherished frameworks. Imagine the scholar in his study, surrounded by star charts and Aristotle's texts, convinced the heavens still revolve around Earth. Outside, telescopes are aimed skyward, and the first glimmers of a new universe are coming into view. He defends the old order with conviction, unaware that the ground beneath him has already shifted forever. Astrology as scientific astronomy. Picture a Babylonian priest astronomer standing on a ziggurat 2,500 years ago. He scans the heavens, marking the rising of Venus before dawn, the position of Jupiter against the stars, the shape of the moon's crescent. To him, this is not idle stargazing, but essential science. The heavens are a vast ledger, recording signs that foretell the fate of kings, harvests, and empires. In that ancient world, astrology and astronomy were not separate disciplines. They were one and the same science, the reading of the sky to understand both nature and destiny. The logic was compelling. The sun governed the seasons, bringing light, warmth, and crops. The moon governed tides and cycles of fertility. Why should the other planets not also shape earthly affairs? If heavenly bodies moved with perfect regularity, perhaps their motions revealed the rhythms of life below. The cosmos was seen as a single interconnected whole, with the heavens influencing the earth like a great clock directing its gears. Babylonians developed elaborate star catalogs and prediction methods, tracking eclipses and planetary conjunctions. Their observations were astonishingly accurate. They could forecast lunar eclipses centuries in advance. But the purpose of this precision was not purely curiosity. It was divination. A king's advisors wanted to know if war would succeed, if famine loomed, if a dynasty was secure. Astronomy served astrology, and both were inseparable. The Greeks inherited this fusion. Ptolemy, in the 2nd century CE, wrote not only the Almagest, the great astronomical text of antiquity, but also the Tetrabiblos, the foundational work of astrology. In it, he linked planetary positions at birth to character and fate. His system wove physics, philosophy, and destiny into one framework. To chart the stars was to chart the soul. For centuries, astrology was the practical face of astronomy. Courts employed astrologers, who used planetary tables to cast horoscopes. Physicians consulted astrological charts to determine when to bleed patients or administer herbs, believing that the stars governed bodily humors. Farmers planted according to lunar phases. To educated Europeans of the Middle Ages, it was obvious that the same science that predicted eclipses also explained human fortune. Astrology's status as science began to weaken only with the Renaissance and scientific revolution. As telescopes improved, astronomers like Tycho Brahe and Johannes Kepler made precise observations that began to separate celestial mechanics from celestial meaning. Kepler, though himself employed as an astrologer, grew skeptical of the practice even as he discovered his laws of planetary motion. Galileo, turning his telescope to the heavens, revealed imperfections, the moon's craters, Jupiter's moons, that clashed with astrology's idealized cosmic order. By the 17th century, physics and mathematics began to replace symbolic interpretation. Newton showed that planetary motions could be explained by universal gravitation without appeal to hidden influences on human lives. Astronomy became a science of measurement and prediction for its own sake, while astrology was increasingly pushed into the realm of superstition. Universities that once taught both dropped astrology from their curricula. The divorce was complete. And yet, astrology never disappeared. It retreated from scholarly halls into popular culture, adapting with each age. Newspapers and magazines still publish horoscopes. Millions read them, sometimes in jest, sometimes with belief. Though modern science dismisses the notion that stars determine personality, astrology endures as a cultural language of meaning, a way to talk about character, fate, and cycles of life. Why did astrology remain persuasive for so long? Because it offered a story of connection. It told people they were not adrift in a chaotic world, but woven into the fabric of the cosmos. The heavens were not indifferent. They spoke, if one had the skill to read them. In an age before germ theory or genetics, this vision was comforting. To believe one's life was written in the stars was to believe life had order. Today, astrology is a forgotten theory in the history of science, but it is also a reminder of how knowledge evolves. Astronomy grew out of it, shedding the symbolic skin while keeping the precision. The same star charts once used to predict the fate of kings became the basis for calculating spacecraft trajectories. In a way, modern astronomy is astrology's child, grown into its own. Imagine again the Babylonian priest on his tower, watching Venus rise. He records it in clay tablets, convinced that its brilliance foretells victory in battle. He is wrong about the message, but right to watch carefully. His notes, passed down, will help future astronomers trace planetary cycles with stunning accuracy. His error is part of our inheritance, proof that even mistaken ideas can carry the seeds of science. Alchemy's philosopher's stone. In a dimly lit workshop of the Middle Ages, a figure bends over a furnace. Glass vessels bubble with strange brews, metals glow in crucibles, and smoke curls toward the rafters. The air smells of sulfur and mercury. On the workbench lies a manuscript covered with symbols, circles within circles, suns and moons, cryptic animals drawn in ink. The alchemist is searching not only for gold, but for something even more elusive, the philosopher's stone, a legendary substance said to transmute base metals into noble ones, and in its highest form to grant immortality. The dream of the stone grew from a fusion of philosophy, chemistry, and mysticism. Ancient Greek thinkers had already speculated that all matter was composed of the four elements: earth, air, fire, and water. If matter shared a common essence, perhaps it could be transformed. The Egyptians practiced metallurgy and dyeing, arts that seemed to change substances dramatically. By the early centuries of the Common Era, this speculation crystallized into alchemy, a discipline that spread through the Islamic world and medieval Europe, promising not just material wealth but spiritual enlightenment. At its heart, the philosopher's stone was more than a recipe. It was a symbol of ultimate transformation. To turn lead into gold was to take what was dull, heavy, and corruptible, and refine it into what was radiant, incorruptible, and pure. Alchemists believed that metals matured within the earth, lead being an immature form destined to become gold over ages. With the stone, they hoped to accelerate nature's process, forcing perfection in the furnace. Legends multiplied. Some said the stone could cure all disease, restore youth, even confer eternal life. It became known as the elixir of life, merging the material with the mystical. Alchemists like Paracelsus spoke of it not just as a mineral, but as a medicine for the soul. The search for the stone became a quest for wholeness, for mastery over both nature and mortality. The pursuit was serious, but also cloaked in secrecy. Recipes were written in riddles, using allegory and metaphor to hide processes from the uninitiated. Sulfur, mercury, and salt became not just substances but principles: the fiery, the fluid, the stable. Alchemical texts spoke of marriages of sun and moon, deaths and rebirths of matter, blackening, whitening, reddening, stages of transformation that mirrored spiritual journeys. For the alchemist, the laboratory was both workshop and temple. Why did the idea endure for so long? Because it fit human hopes. To make gold was to solve poverty. To heal all wounds was to conquer suffering. To live forever was to defy death itself. In an age when science and mysticism were not cleanly separated, the stone embodied the promise that ultimate knowledge could deliver ultimate power. But as chemistry advanced, the philosopher's stone began to fade. Careful experiments revealed that metals could not be transmuted by simple recipes. The discovery of elements like oxygen and hydrogen showed that matter was more complex than ancient theories suggested. By the 17th century, alchemy's reputation declined. Isaac Newton himself studied alchemical texts in secret, searching for hidden truths, but in public, chemistry moved toward measurable reactions and reproducible results. The stone became a metaphor rather than a goal. Yet its legacy is profound. Alchemy, for all its errors, developed techniques of distillation, crystallization, and metallurgy that laid the groundwork for modern chemistry. The laboratory glassware and furnaces of today are descendants of the alchemists Alembic and Aether. Even the language of transformation, based to noble, impure to pure, survives in the way we describe science, art, and even personal growth. The stone itself has become one of the great archetypes of Western imagination. In literature, it appears from Chaucer's Canons' Yeoman's Tale to modern fantasy. It symbolizes the quest for ultimate knowledge, the desire to bridge the gap between matter and spirit. To seek the philosopher's stone is to seek perfection, whether in gold, health, or the self. Imagine again the alchemist at his furnace, sweat on his brow, eyes fixed on the glowing crucible. He is convinced he is on the verge of discovery. He is wrong in detail. He will never make gold, never distill immortality, but he is not wrong in his longing. His dream is our dream too, to transform what is base into what is noble, to find in the world and in ourselves the spark of perfection. The philosopher's stone is forgotten as science, but remembered as symbol. It reminds us that every search for knowledge carries with it a hunger for transformation, and that even failed quests can leave behind treasures. The alchemists did not find the stone, but they helped lay the foundation for the chemistry that would explain why it could not exist, and in the process, they gave us a story that still glows, like gold, in the human imagination. Flat Earth cosmologies. Stand on an open plain and look around. The horizon seems perfectly level, stretching outward like the edge of a great disk. The ground beneath your feet feels steady and unmoving. To the senses, Earth appears flat. And for much of human history, this everyday impression shaped cosmology, the belief that Earth was not a sphere but a plane, sometimes endless, sometimes bounded by walls, mountains, or oceans. These flat Earth cosmologies were not simple ignorance, but complex, meaningful worldviews that blended observation, myth, and philosophy. The oldest cultures recorded their visions of a flat Earth in sacred texts and stories. The Mesopotamians pictured the world as a flat disk surrounded by water, covered by a dome of sky. The Hebrews, drawing from similar traditions, described the firmament in Genesis, a solid vault holding back waters above. The Egyptians imagined Earth as a flat surface beneath the arched body of the goddess Nut. To the Norse, the world was a flat realm encircled by a cosmic sea and the great serpent Jörmungandr. These were not idle fancies. They were coherent cosmologies linking earth, heavens, and underworld into a single sacred structure. In Greece, early philosophers debated the matter. Homer's epics describe a flat world encircled by the river Oceanus. Later thinkers like Anaximander proposed Earth as a cylinder floating in space. The idea of a spherical Earth gained traction only gradually, supported by Pythagoras, Plato, and Aristotle, who cited evidence such as Earth's curved shadow on the moon during eclipses and the way ships disappeared, hull first over the horizon. By the time of Eratosthenes, who measured Earth's circumference in the 3rd century BCE with remarkable accuracy, the spherical model had become dominant among educated elites. Yet flat Earth views persisted among many cultures, especially where mathematical astronomy had less influence. In the Middle Ages, some popular writers in Europe still described the world as flat, though most scholars accepted the sphere. In parts of Asia, Africa, and the Americas, traditions continued to describe Earth as level, sometimes resting on the back of animals, turtles, elephants, or serpents. These images carried symbolic power, linking stability with cosmic order. The persistence of flat Earth cosmologies was not simply stubbornness. For the ordinary observer, the evidence of daily life contradicted the sphere. If Earth were round, why did people not fall off its underside? Why did the ground feel steady, not curved? Why was the sky spread like a dome overhead, not wrapping around a globe, without ships circumnavigating or telescopes scanning space? The flat model felt more natural. Medieval Europe, contrary to modern myth, did not generally believe in a flat Earth. Most scholars, guided by Aristotle and Ptolemy, accepted sphericity. The story that Columbus set out to prove Earth was round is largely a legend. Educated people of his time already knew it was. But in popular imagination, flat Earth imagery lingered, partly because it aligned with scriptural interpretations, partly because it seemed to match experience. The final decline of flat Earth cosmologies came with exploration and modern science. Circumnavigation by Magellan's crew in the 16th century proved the globe by direct experience. Telescopes revealed Earth as a sphere among spheres. Newton's law of gravitation explained why planets were round, pulled into spheres by their own mass. By the modern era, the flat Earth was relegated to folklore, curiosity, and eventually pseudoscience. Still, it has never fully vanished. In the 19th century, a few fringe figures revived flat Earth arguments, claiming that photographs and astronomical evidence were faked or misinterpreted. Even today, small groups of flat Earth believers persist, often as defiance against authority rather than genuine science. Their presence is less about cosmology than about skepticism of institutions. Ironically, the flat Earth, once the common-sense view, has become a symbol of radical doubt in an age of overwhelming evidence. Why does the idea continue to haunt us? Because it speaks to the limits of perception and the power of narrative. The world does look flat. The sun does seem to rise and set. Trusting only the senses, one might never guess the truth. It took centuries of careful reasoning, measurement, and daring voyages to overturn the intuition. The flat Earth reminds us that common sense can mislead, that truth is not always what appears obvious. Imagine an ancient priest standing beneath the dome of stars, tracing constellations on a sky he believes solid. He draws maps of a world encircled by oceans, confident that this is the shape of reality. He is wrong in detail, but not in spirit. He is trying to make sense of the infinite with the tools at hand, weaving order from mystery. His cosmology is forgotten, yet it is part of the long human journey toward understanding, a journey that continues still as we seek new truths beyond what seems self-evident. Hollow moon theory. Look up at the moon on a clear night. Its pale light bathes the landscape, its surface marked by seas and craters that invite the imagination. To astronomers, it is Earth's companion, a rocky sphere about a quarter our size. But in the 20th century, some proposed a stranger vision that the moon is not solid at all but hollow, an artificial construct, perhaps even the relic of alien engineering. This is the hollow moon theory, a modern cousin of the old hollow Earth speculations. The idea emerged after the space age began. When the Apollo missions placed seismometers on the lunar surface, scientists recorded the vibrations caused by meteor impacts and deliberate rocket crashes. To their surprise, the moon rang for far longer than expected, sometimes for hours, like a bell struck in vacuum. Though mainstream geologists explained this as the result of the moon's unique structure and lack of water to dampen vibrations, fringe thinkers seized on the data. If the moon rang like a bell, perhaps it was hollow. The theory quickly leapt beyond geology into speculation. Some writers proposed that the moon was a giant spaceship placed in orbit by advanced beings in prehistoric times. Others argued that it was a shell built to observe Earth, or a base from which extraterrestrials monitored humanity. A few suggested that myths of gods or two suns from ancient cultures hinted that the moon had been deliberately installed in our skies, altering Earth's tides and stabilizing its climate. Earlier echoes of this idea existed too. In the 1960s, Soviet scientists Mikhail Vasin and Alexander Sherbakov published a paper in Sputnik magazine suggesting the moon might be a hollowed-out planetoid, engineered by unknown intelligences. Though never mainstream, their proposal fed the popular imagination at a time when space exploration was revealing the moon in unprecedented detail. Science fiction picked it up eagerly, weaving tales of alien structures inside the lunar crust. Why did the hollow moon idea resonate? Partly because the moon is uncanny. Unlike most moons in the solar system, it is unusually large relative to its planet. Its orbit produces perfect eclipses, covering the sun's disk precisely, a coincidence that feels too neat to some. Its face is locked toward Earth, as though placed deliberately to watch us. For those inclined to see design in the cosmos, these features made the hollow, artificial moon a compelling thought. Science, of course, tells a different story. Geological evidence shows the moon is not hollow but differentiated, a crust, a mantle, and a small core shaped by its violent history. Seismic data from Apollo missions, later reanalyzed, revealed internal layering consistent with a natural satellite. The ringing effect was unusual but not mysterious, caused by the moon's dry, fractured rock transmitting seismic waves efficiently without the damping fluids present on Earth. Far from being hollow, the moon is scarred and dense, its interior mapped in detail by modern missions. Yet the hollow moon theory endures in conspiracy circles. Some link it to UFO lore, claiming the moon hides alien bases, or that NASA concealed evidence of structures during Apollo. Others fold it into broader myths of ancient civilizations, suggesting the moon was engineered to stabilize Earth's tilt and make life possible. In these stories, the moon is not just a rock, but a deliberate artifact. Why does such a theory persist, despite overwhelming evidence to the contrary? Because it speaks to deeper anxieties and longings. The moon has always been a mirror of human imagination. In it we have seen gods, lovers, lunacy, and mystery. To imagine it hollow is to imagine that we are being watched, that our place in the cosmos is not accidental but observed. It transforms the cold, dead rock into a stage for hidden drama. And even as pseudoscience, it reflects a truth about wonder. The moon is extraordinary, shaping tides, stabilizing Earth's axis, influencing life in profound ways. Its presence is so crucial that imagining it artificial is less a scientific hypothesis than a mythic attempt to explain its importance. Picture an Apollo astronaut in 1969, standing on the Sea of Tranquility, gazing at Earth rising in the black sky. He knows the moon is dust and stone, yet he feels the uncanny silence, the weight of its presence. Back on Earth, readers pore over strange theories, convinced there must be more. They are wrong about the hollowness, but not wrong to sense mystery. The moon is ordinary matter, yet extraordinary in meaning. The hollow moon theory is forgotten as science, but it lives on as folklore of the space age. It shows how even in an era of rockets and seismographs, the oldest human impulse persists to look at the sky and imagine secrets inside the light that shines back. Canal theories of the nervous system. Close your eyes and imagine the body as early anatomists once saw it, a network of hollow tubes branching through flesh, carrying mysterious fluids that made the difference between motion and stillness, thought and silence, life and death. Long before the nervous system was understood as a web of electrical impulses and chemical signals, physicians believed that nerves were literally canals, tiny pipes through which subtle fluids flowed, animating the body like water through irrigation ditches. The roots of this idea stretch back to antiquity. Galen, the great Roman physician of the 2nd century, taught that the brain produced animal spirits, ethereal vapors distilled from blood. These spirits, finer than breath but more substantial than thought, traveled through hollow nerves into muscles and organs. When the spirits flowed, the body moved. When they were blocked, paralysis or illness followed. For centuries, this vision dominated medicine, nerves as channels, the brain as furnace, the body as hydraulic machine. In the Renaissance, the canal model grew more detailed. Anatomists dissected the human body with greater precision, tracing the white cords of nerves branching from the spine. They saw them not as bundles of fibers, but as hollow tubes. Under the influence of hydraulic engineering, fountains, pumps, aqueducts, they imagined the body as a pressurized system. Muscles swelled when fluids rushed into them, just as water filled the pipes of a fountain. Thought itself was pictured as a flow, like a valve directing currents from brain to limb. The great philosopher and mathematician René Descartes embraced this view in the 17th century. He compared the body to a machine, its motions caused by fluids streaming through nerve canals. A flame touching the foot, he wrote, sent animal spirits rushing to the brain, which in turn redirected them back through nerves to contract muscles and pull the foot away. For Descartes, the soul remained distinct, but the body could be explained in terms of hydraulics, a mechanical puppet animated by hidden streams. This model was compelling because it matched the technological metaphors of the time. As water wheels turned mills and hydraulic machines performed feats of motion, it seemed natural to imagine the body working the same way. Doctors could even explain mental illness as disturbances in the flow, too much fluid, too little, or currents diverted into wrong channels. The nervous system was less an electrical network than a system of plumbing. Yet the canal theory struggled as observation advanced. By the 18th century, microscopes revealed that nerves were not hollow tubes but bundles of fibers. Experiments showed that severed nerves did not release fluids, nor could any liquid be traced coursing through them. Meanwhile, discoveries in electricity offered a new metaphor. Scientists like Luigi Galvani found that electric sparks could make frog legs twitch, suggesting that nerves carried not fluids but currents. The hydraulic model gave way to the electrical one, and the canal theory began to fade. Still, the imagery of flow persisted. Even today we speak of circuits and channels in the nervous system, echoing the old canal metaphors. Neuroscience describes ions moving through channels in cell membranes, a more accurate but still fluid-like vision. In some sense, the canal theory was not wholly wrong. It intuited that movement in nerves was directional, that something passed along them, that blockages could cause dysfunction. The details were flawed, but the instinct to imagine flow was not. The story of canal theories also reminds us how science draws from culture. In an age of aqueducts and fountains, nerves became pipes. In the age of electricity, they became wires. In the digital age, we describe them as circuits, processors, networks. Each metaphor illuminates but also limits. The canal theory was a necessary step, a bridge of imagination from ignorance toward the truth. Why did it endure for so long? Because it offered an image both visible and plausible. Anyone could see fluids moving through pumps and pipes. Anyone could see blood coursing through veins. It was easier to imagine a subtle fluid animating nerves than to conceive of invisible electrical potentials. The canal theory lasted until a better metaphor and better evidence replaced it. Picture a Renaissance physician explaining paralysis to a patient. "The channels are blocked," he says. "The spirits cannot reach your limbs." He believes this sincerely, drawing comfort from an image that feels orderly, mechanical, solvable. He is wrong, but his wrongness is part of a lineage of questions. Without canals, no one would have looked for the flow. Without the flow, no one would have imagined electricity. Without electricity, no one would have reached the synapses and ions we describe today. The canal theories of the nervous system are forgotten as science, but remembered as metaphor. They remind us that knowledge is always provisional, framed by the tools and symbols of its age. Once, nerves were canals. Now they are circuits. In the future, they may be seen in ways we can hardly imagine, but the human need to explain, to find the hidden currents beneath sensation and thought, remains as steady as the flow those early physicians once believed they could see. We've wandered through theories that once lit the imagination of entire eras. Each was wrong in its way, yet each carried a spark of human wonder. They remind us that knowledge is not a straight line from ignorance to truth, but a long path of stories, bridges we build and later leave behind. In their failures, these theories still gave us something lasting. They sharpened experiments, inspired questions, and showed how deeply people long to connect the mysteries of life with patterns they can grasp. What we dismiss as forgotten today was, for someone once, the cutting edge of hope. As you drift from these echoes of old science into the quiet of your own thoughts, hold on to the reminder that even mistakes are part of discovery, that curiosity itself is never wasted. And if you'd like to keep exploring these journeys with me into philosophy, psychology, and the sciences we've almost forgotten, consider subscribing, leaving a thought in the comments, or simply giving this video a small sign of appreciation. Thank you for listening, and until next time, may your questions remain as alive as the answers you seek.